Started. Hi, everyone. Welcome to Mars Secondary Alteration Processes. If you're here to learn about alteration on Mars, you're in the right room. If not, it'll be a fun session regardless. I am James Haber. I am one of the chairs today. My fellow chairs are.
Yeah, I'm Steve Roth from Arizona State University.
And I'm Thanos Kladaris from Purdue University.
And I'm a postdoc at Smithsonian Air and Space Museum. So each session, each talk is 10 minutes. There'll be four 10-minute talks followed by 20 minutes of Q&A. There will be a yellow light when the speaker has reached 8 minutes, and in which case you will have 2 more minutes, and you will be told to stop after 10 minutes so that we can keep things moving smoothly. If you are a virtual presenter, you will not be able to see a timer, but we will give you a verbal reminder when 2 minutes are left in your session, in your talk. Also a reminder, if you signed up to, or if you have not signed up, the Dwornik judging is continuing on. We have some students in today's session and in the poster sessions in the afternoon as well. So please sign up. And if you have already, please remember to do your judging. Anything else? And we've got a couple more minutes before our start time. If the first speaker can make sure they are checked in with AV, and reminder for all speakers to go up before your talk and check in with AV to get mic'd up.
So the timing starts as soon as so they have to be mic'd up ahead of time.
Yes, and mic up ahead of time because timing starts when it starts.
So if our first speaker can make their way up, it's Ben Bultell. Is Ben here? First speaker, Benjamin Bultell. Online. Okay, we've got him presenting. Is Ben Bultell online for virtual? And we'll find out.
Yeah.
Sorry for the delay, folks. We have some confusion about whether this person is in person or virtual, and apparently virtual.
That's the most. We can't do anything else.
What's he?
They said that.
Okay, so this is a little piece of information for those who have registered for this meeting. If you registered for in person and you're virtual, you won't get to talk, apparently. So this Ben was registered for in person and now is expecting to be able to give a virtual presentation, which may not be possible. Huh? Sure. In 200 years.
Hmm. Can you hear me? And I
Yes, we
cannot hear
can
you.
now. You can fit a 10-minute talk into 7 minutes. Let her go. Here we go. Ben Patel.
I cannot hear you any longer.
Can you hear us, Ben?
Okay. I see my slide. I think you can hear me, but I cannot hear anything. So I have no idea if I should start.
Yes, keep going. We can hear you.
What? Okay, so I guess you can hear me now. I'll try to make quick. Sorry to make you late. So the idea with this work was to try to answer to the question, how could we produce magnetite to explain all the magnetic anomalies that we see at the surface of Mars? And basically the best candidate to explain these magnetic anomalies are pyrrhotite and magnetite. Next slide, please. Yes, thank you. Yeah, next slide, please. So one of the best explanations that people suggest most of the time to explain all the magnetite that should be present inside the Martian crust is through serpentinization. And basically the idea is that because you have a lot of olivine and pyroxene in the Martian crust, you alter it with water and you produce a lot of serpentine, but also some magnetite. But it's not as simple as that. It's not like just make serpentine and you will produce magnetite, because the iron 3 plus that is going inside magnetite can also go inside the serpentine itself, or a bunch of other clays that can produce during serpentinization. So if you go to the next slide, please. So it's not our motivation by doing new models is try to see if when we change the temperature of the hydrothermalism, or if we change the magnesium number of the olivine, we will favor or disfavor the formation of magnetite. And we wanted to try different type of crust composition, not just olivine and pyroxene alteration. Next slide, please. So the first step of this work was to try to determine how much magnetite you need to explain the strong magnetization that you see inside the crust. But give us the graph that you will see in the next slide, please. So basically, what you see with this graph is that you have a bunch of different type of thickness of a magnetic layer that are tested, and it corresponds to different amount of magnetite that is needed to match the magnetization that is in the crust. And basically, you need like few weight percent of magnetite in a 10-kilometer thick crust to buried at 20-kilometer depth to explain the magnetization. And you need around like 1% of magnetite in the crust to explain what is seen at inside landing site. Next slide, please. So then the next step of this work is to do some geochemical modelings. And you can see here that we tried a lot of different type of rocks, from really mafic with dunite to really felsic, like the trachyte. Then we can try different type of fluid composition. We tried with pure water, or like composition that is often used in geochemical models for hydrothermalism on Mars. You can add CO2 or sulfur or chlorine or whatever elements in the fluid, and you can try different type of water to oil ratio from 1 to 1,000 in our models. You can heat the fluid at different type of temperature, and we tried at like 100 degree and 200 degree. Next slide, please. And you can go to the next slide and to the next slide. And so basically what you get in the result is the prediction of the amount of the type of minerals that are formed. And here I'll show you an example with what is formed with when you alter like a dunite, typical of what you find on Earth, with a water to oil ratio of 1 and temperature of 200 degrees. So if you want to have like 1 or 2% of magnetite from that, you need to alter at least 0.5% of a rock. Next slide, please. And next slide. So you can see that if you lower the temperature, you lower the amount of magnetite that you produce. And if you change the ion to magnesium ratio in the dunite, you will change also the amount of magnetite that you produce. Next slide, please. So here you have an example then with pyroxenite, so less olivine in the rock, and you see that you need a really high water to rock ratio to have a high amount of magnetite. Next slide, please. And you see that it can give the same thing with chagotite. And next slide, please. And basically the idea is that if you test like different rock, like differentiated rock, more felsic rock, you will produce less magnetite, but if you consider only olivine or pyroxene. Next slide, please. And basically I wanted to show you where is going the iron 3+ when it's not going in the magnetite. Basically it's going a lot in the clays, like in serpentine, that is really iron rich in this type of models. Next slide, please. And this graph show you actually that if you do this kind of hydrothermalism with something different than dunite, you need like very high water to rock ratio of 100 or 1,000 with the alteration of pyroxenite or chagotite to reach high amount of magnetite after the alteration. So basically, if you want to have a lot of magnetite with altering something different than dunite, you need a lot of water. You don't need just a fracture inside the crust filling with water. You need a big aquifer and mature hydrothermal system to produce a lot of magnetite. Next slide, please. And I wanted to talk to you a lot about what kind of minerals you product when you do some kind of models like with chagotite-like composition at the beginning. And here you have an example of what is happening with this type of chagotite type of rock with water to oil ratio of 10 or 100. And the idea was to show you that you produce a type of minerals that we actually detect from the orbit. So you predict the formation of chlorite, saponite, some carbonate, some talc, a bit of serpentine. And this is kind of coherent with what is seen from orbit in hydrothermal system. Next slide, please. And so what you need to keep in to remember from this talk is that
we need to end this talk.
Try to predict how much magnetite is needed in the crust to match the magnetic field that is seen from orbit and in situ. You need a few percent of magnetite, and basically you need to alter pyroxenite or chagotite type of rocks with a lot of water in the system to reach this kind of amount of magnetite.
Weathering in shaping clay deposits on Mars. Take it away.
I thought I would suddenly be the first speaker. Yeah. Hi everyone. So here's the clicker, right? So the next slide. Okay. Okay. So I know how to use. Okay. So hi everyone. I'm Jiawei Wang from Cornell University. Today I would like to present our recent modeling work on chloride-driven oxidative weathering and its role in formation of oxidized clay deposits on Mars. There are very diverse secondary minerals on Mars, and among all these secondary minerals, there's a major one that is iron magnesium-rich smectite. There are two important features about smectite on Mars. The first is the compositional stratigraphy, characterized by this aluminum silicate-rich clay overlying iron magnesium-rich phyllosilicate, mostly smectite. Additionally, 78% of the smectite on Mars contains iron 3, which is the oxidized form of iron. And these two features altogether suggesting that significant oxidative weathering could have occurred on Mars. For such intense oxidation to occur, a huge number of oxidants are required. While on Earth, oxidative weathering is mostly driven by free oxygen. This is not likely on Mars because the oxygen partial pressure there is extremely low. Under these conditions, the oxidation on Mars could be much slower than that on Earth. There have been experimental studies synthesizing iron 3 bearing clay at lab, but mostly with pre-existing iron 3 or oxygen. There are other studies exploring alternative oxidation pathway like alteration by hydrogen peroxide or alteration by UV radiation, but they both have their limitation. In summary, the abundance of iron 3 bearing clay and the lack of efficient oxidants on Mars are paradoxical. To solve this paradox, alternative oxidants, oxychlorine species are proposed. Oxychlorine species, including chlorate and perchlorate, can be generated through photooxidation. And perchlorate has been detected on Mars with high abundance. Additionally, experimental studies have demonstrated that chlorate can rapidly oxidize iron 2 to iron 3 under aqueous conditions. So having a stable formation pathway, high abundance, and strong oxidizing capacity, chlorate has great potentials. My question is, what's the role of chlorate in formation of iron 3 rich oxidized clay deposits on Mars? To answer these questions, we conducted reactive transform modeling, which is a forward modeling technique. We started from the basaltic bedrock, leached it with a continuous flow of fluid, simulating the infiltration for 1 million years. And during the weathering, there are dissolution and precipitation of minerals, corresponding porosity changes, and oxidation of iron 2 to iron 3. The modeled weathering profiles are then compared with the observed stratigraphy to test if our pathways and parameters are favorable. The table on the right is a summary of the variable tested for this study. The results of this study will show as stacked plots, and here's an example. So the y-axis is the regolith depth. And at a certain depth, if we draw a horizontal line like this, and for example, the volume fraction of the augite can be inferred from the length covered by this dark gray color like this. And similarly, the fractions of other minerals can be read from the diagram together with the porosity. So in one word, larger the area, higher the abundance. It's worth noticing that nantronite in this study refers to the iron 3 rich oxidized clay, and the saponite is the iron 2 bearing reducing ones. Okay, so for the first part, we investigated controls of acidity by running the model at different pH values. As we can see from the results, the weathering fronts become steeper at lower pH, and suggesting enhanced weathering rate under acidic conditions. Moreover, we can see that the abundance of this like sandy brown region, which refers to the nantronite, is also elevated at lower pH. And this is because the oxidizing potential of chlorate increases with acidity. If we look at the general pattern of our modeled profile, we can see aluminum-rich clays is at the top, and iron magnesium rich phyllosilicate lying beneath it, which is very consistent with the compositional stratigraphy. And we are very excited when we first see the results. Moreover, we conducted modeling with variable chloride concentration and oxygen partial pressures to compare the roles of these two potential oxidants. So as we can see from the figures, nitronite formation is very sensitive to chlorate. Even a trace amount of chlorate, as low as 10 micromole, can induce formation of nitronite. And the abundance of nitronite is highly dependent on chlorate concentration from the left to the right. So it seems like chlorate has done a good job. Then let's see the performance of oxygen. And we can see that there's no production of nitronite until the oxygen level is increased to around 0.01 bar, which is already a relatively high assumption. And if we compare chlorate and oxygen in terms of producing oxidized clay, we can see that chlorate at a concentration less than 0.1 millimole is equivalent to oxygen at 0.1 bar, suggesting that chlorate is a much more efficient oxidant. We then evaluate the influence of temperatures. And so when we usually think weathering is much slower at lower temperature, our model suggests that the breakdown of stephanite is actually accelerated at lower temperature. And this is because thermodynamically, stephanite becomes less stable with the decreasing temperature. What is more interesting is that when temperature drops to below 15 degrees Celsius, our model indicates extensive formation of amorphous silica, which is interesting because silica has been detected at multiple sites correlated with aluminum clay. And our model suggests this formation is preferential at low temperature. Lastly, we combine different water flow rates and temperatures to to test weathering under different climate scenarios, either cold or warm, or dry and wet. So the outcome shows that wetness largely determines the thickness of aluminum clay deposits. If you get like more water, you get enhanced weathering, and then you can make like thicker aluminum clay layer. Just like if it is dry and then it's much more narrower. Our model also shows that amorphous silica is only produced under cold and dry conditions, suggests the great potential of amorphous silica as a climate indicator for early Mars. As a summary, here's a conceptual model of this study, and then the chloride is photooxidized to oxychlorine species, which later induced the oxidative weathering of the basaltic bedrock, forming this regolith with 1, 2, 3, 4 layers and 3 weathering fronts. The first is stephanite formation front, which is basically the breakdown of primary minerals in bedrock and formation of iron 2 rich stephanite. The second one is the nitronite formation front, which is the oxidative alteration of stephanite and formation of nitronite. At the top is kaolinite formation front. Continuous leaching of nitronite will eventually transform these minerals to kaolinite, which is the stable phase at Martian surface. And this is the whole conceptual framework. And here's the main takeaway of these studies. In the end, I would really like to say I'm extremely new to this field, and it's my first LPSC. I barely started my research on Mars half a year ago. Yeah, and it's been an amazing journey, and I'm really feels like honored to have the opportunity to share my work with you who are the pioneers and experts in this field. Yeah, so, and I do hope I can contribute my expertise in modeling and experiments to this field in the future. And once again, I'm Jiawei Wang from Cornell University. Thanks for listening.
Thank you. Okay, next up is my co-chair, James Haber, with the talk on linking alteration minerals to aqueous activity in Martian fan deposits. Take it away.
Thank you for that introduction. So I'll get right into it because you already said my title introduced me. So fan deposits on Mars are generally thought of splitting up into alluvial fan deposits, which are deposited subaerially, and delta deposits, which are subaqueously, or in lacustrine environments. And these are, apparent on Earth, so you can see in the orbital data, and very similar on Mars. And these are, pretty ubiquitous across Mars, evidence of prolonged and episodic aqueous activity into even the early Amazonian period. And alteration minerals are often found in a lot of these deposits. These alteration minerals are evidence of aqueous activity, things such as like clay minerals and hydrated silica and sulfates. And so understanding where and how these alteration minerals form in these deposits, did they form maybe in the catchment region, and they're detrital because they were just, eroded out of the crater wall or fluvial valley and transported into the fan deposit, or maybe they formed during transport or even after deposition in the basin during diagenesis. And so understanding where and how these alteration minerals formed is important for constraining the timing of aqueous activity and formation of these deposits on Mars. So in this study, we focus on Xanthe Terra. It's a very fluvially dissected region. It has a lot of these fluvial valleys that end up in impact craters, which make great places for alluvial fans to form and delta deposits to form. It's also a pretty dusty area, so the chrism coverage is generally mixed, but we do have 5 FAM deposits that we'll be talking about in this study that have chrism coverage that is dust-free enough that we can study alteration mineralogy in the fan deposits and also some of their catchment and or watershed regions. And so we compare where we do have coverage of the catchment watershed and the fan deposit, we compare the mineralogy in order to understand, are some of these minerals that we see in the deposits detrital, were they transported from the catchment region, or maybe they're authigenic, do they form in place? So first we'll start with this lovely scarp-fronted deposit in northern Xanthe Terra. So this scarp-fronted deposit has this sort of frontal scarp, we call it, and that we think indicates that it formed in standing water, so it's probably a deltaic feature. Here we have a chrism composite image. This is formed by placing these different absorption band parameters in the red, blue, and green color bands. So for here, red is absorption at 2.3 microns, which is usually consistent with iron magnesium clays. Green is 2.2 microns, which could be consistent with aluminum phyllosilicate or hydrated silica. And blue indicates absorption at 1.9 microns, which is due to hydration. And so by combining these, we can see that, for example, this magenta region, combination of the red and the blue absorptions, is likely consistent with iron magnesium smectite, such as like notronite over here. And we see this stand out pretty well in the watershed region. You may have some very faint features in the fan deposit, but these could have been changed due to mixing in the fan deposit with other detrital minerals. So zooming into the catchment, we can actually have some nice high-rise coverage as well. So we can see really in the crater rim, this watershed wall, where these iron magnesium smectites likely eroded. And this is, eroding from a Noachian crater. So it's probably this, Noachian clay deposit. And because we see it very faintly in the fan deposit where we do see this clay, it's probably going to be detrital. However, we also see a couple places where we may see signatures, absorptions closer to 2.2 microns. And so that could be more consistent with like aluminum phyllosilicate. And we see this in the frontal scarp of the fan in these eroded layers and also in a channel on the fan deposit. And so these possibly aluminum phyllosilicate minerals could be authigenic or formed in place. Moving on to another fan deposit, this time it's in a crater that is at the end of this Tyrus Vallis. Tyrus Vallis actually ends in a delta deposit, which you may be able to see small over there. There's no chrism coverage, unfortunately, of this delta deposit, so we didn't look too much into it, but this formation evidence is evidence of a possible lacustrine environment in this crater. But previous studies have found that this alluvial fan that we'll be talking about in the northeast part of this crater was likely one of the last things to form in this sequence of events. So probably after this paleolake dissipated. And we can see in the chrism data that there's absorption features that are pretty consistent with hydrated silica, both in this alluvial fan as well as nearby on the crater floor or the basin. There are some slight differences, but in general, because we don't have the same chrism coverage of the watershed or catchment region of this fan, it's hard to say conclusively whether these minerals are authigenic or maybe they could have been eroded and in place there. Further research will look into getting deep into the imagery and features to understand do they have any other symbolism or morphological things that are consistent with an authigenic formation. Moving on to this lovely stepped or terraced fan deposit in Chemi Shell Crater. Again, this sort of step feature and frontal scarp indicates that it was probably formed in a lacustrine environment, so potential delta. It's also the source of this larger Nanady Vallis, so probably a lot of source water in the area. And here zoomed in, again, with the same chrism composite, we can see this very bright hydrated silica feature stand out. And previous studies have also looked at this feature, and because it is so bright and smooth, in addition to it being sort of confined in a single layer, and not really seeing any evidence of hydrated silica within the watershed or catchment region. We just see this iron magnesium smectites. This hydrated silica that we see very clearly in the fan deposit and in this just below sort of linear-ish feature that is very bright and shiny. We think that this is probably an authigenic deposit. So this formed either during or after the deposition of the fan sediments. Next, we'll move on to this crater with a lovely pair of alluvial fans in Shalbatana Vallis, which again, we can see in the chrism data, clear features related to iron magnesium smectite in both the fan surface as well as the crater walls. So this is, eroded from Noachian terrain, and these iron magnesium smectites that we see in the fan itself for the fans themselves are probably going to be detrital, as we see very clearly that they're eroded from this crater wall where these features stand out clearly. And some differences between, the absorption features may be due to some mixing or maybe even authigenic mineral formation. We also see this very bright deposit in the basin that also stands out as iron magnesium smectite. And so this could be, maybe later formation, but is similar enough that this could also be a detrital clay deposit. Finally, we have another stepped fan deposit with a frontal scarp, indicating that it was probably a delta. And there's also other people have mapped a possible shoreline in this Dogana crater in Ophir Planum, suggesting that there may have been a lacustrine environment in this crater. And looking at the chrism again, we see hydrated iron magnesium smectites in this short fluvial channel, as well as in parts of the fan deposit. This indicates that they're probably going to be detrital clays. We don't see strong evidence of any authigenic minerals forming here, but further work will look into more parts of this fan deposit and understanding where and how these could have formed. So in conclusion, we see a lot of variety of alteration and aqueous activity in these fan deposits in Xanthe Terra on Mars. This indicates that there was prolonged and episodic aqueous activity in this region, and a lot of the times the alteration mineralogy is somewhat consistent with the morphology of these features. So these stepped or terraced fan deposits have more evidence of some kinds of alteration, like the bright hydrated silica feature in Chemi Shell Crater, and so this is consistent with there being more water and water sticking around for longer in these possible lacustrine environments. And again, also the importance of having chrism coverage or being able to understand both the composition of the catchment region as well as the fan deposit, which we were able to do for most areas, but where we couldn't, it's harder to say whether things are definitely authigenic or detrital. So we're going to continue this work by expanding the study more and looking at fans elsewhere on Mars and comparing their compositions between their catchments and their watersheds to the fans and depositional basins. This will help us, build a better framework for understanding the alteration of fan deposits and fan sediments on Mars. And this will also, of course, help contextualize the traverse of the samples returned from the Jezero fan deposit eventually. And we're also looking into Earth analogs such as Iceland for a potential comparison to what we see on Mars in similar fan deposits on Earth. And with that, I will take any questions during the Q&A. Thank you.
Perfect. So next up is a talk originally from Brad Garchinsky, now given by Anne Olilla, summary of rock coating observations on Mars from past rover missions. Take it away.
Thank you. Is this the thing? Oh, I think I went, oh, I don't know how to use this. So can we go back? Do I go back? Okay, I'm sorry. Okay, yes, Brad sends his regrets for not being here today. He really wishes he could, but I will do my best on his behalf. This is kind of a general topic here, rock coatings on Mars. We've seen several types already, but for sake of time, we're going to focus just on these purplish type coatings that we've seen. There's an example in this SuperCam image on the right-hand side where you can see these purple splotches. And so that's what we're going to focus on today. So what are rock coatings? So they are pasted on material that form on the surface of rocks. They form in a variety of environments, but on Earth, they've been most well studied in rock varnish. So we have an example of rock varnish here. So it's a manganese and iron-rich oxide-rich coating on top of rocks that has a significant fraction of clays. So here's an example from Arizona. And so you can see the coating in this section here and in the association with microbes. And so for this type of coating, the literature has progressed over time to become more into the theory that the manganese enrichment is due to biological mediation. And so this is something that is a very typical type of rock coating on Earth. There's also silica glazes. This is an example from Hawaii that's also associated with the manganese iron rock varnish. From what I can see in the literature, these purple type coatings are a little bit more rarely studied, but when you go outside into the world, you will see them. I'm from New Mexico, and before we started seeing them on Jezero, I had been walking all over these and didn't even realize it until I was like, hey, there's purple coatings all over my backyard. And so here's an example from the Atacama Desert of a purplish coating. It's a little hard to see in these examples. But we recently did a field trip there to study these halite salt nodules. And when we walked up to this sulfate hill, we saw purple coatings all over these rocks. We went a little bit farther north into a more arid and less hyper-arid region, and there was tons of purple coated rocks. So they are quite ubiquitous in certain environments on Earth. So where do we see them on Mars? So they've been first, they were identified in previous missions, but in Jezero, they were so prevalent that it really became a very interesting scientific topic. So when we landed in Jezero right around here, we first spotted these very quickly. This is a Watson image of the Natani target, and you can see these purple coatings when the dust is blown away. And then as we went throughout this traverse to the south, we kept encountering these. Here's another Watson image of the Bellegarde target. You can see where it's sort of fractured. It's perhaps a millimeter or two thick in this area, forming in this sort of fluted low area. And then these purple dots identify where we've seen them throughout the traverse. And so we've seen them, I only updated the map up to the public release, but we have continuously seen these throughout the rest of the traverse. This is an interesting target called the Tower of Set. This is a SuperCam image right here. And so all of these black points hit the black coating or the dark purple coating, and then the one hit the white coating. So we'll go through some of the data that we've collected with the Perseverance rover. So this is the Mastcam-Z data. So in the multispectral Mastcam data, you can see in this decorrelation stretch, which is these wavelengths right here, you can see it stands out quite significantly. And then in the spectra over here, you can see a comparison of the bedrock to the fine regolith, the coating with the dusty fine regolith in the dust. And you can see that there is a 528 nanometer absorption that's consistent with ferric oxides. And the spectra are quite similar to the dust and fine regolith. In the SuperCam VisIR data, you can see in this target Villette, where we analyzed in this paper by Lucia Mendon, there is a 1.9 micron absorption feature, and it is very similar to dusty targets and this dust spectrum right there. And it exhibits that weak hydration. In the SuperCam laser-induced breakdown spectroscopy chemistry data, along with the acoustics data, this circle is a little offset here, but again, going back to that tower of Set, you can see right there, this is where the chemical composition falls in the silica, aluminum, calcium, sodium, potassium, iron, magnesium ternary. And then the one point that struck the underlying white material is significantly enriched in aluminum compared to that. But the coatings tend to cluster around 45 weight% silica, 10 weight% aluminum, and are slightly elevated in sodium and titanium compared to most targets. There's also likely to be a component of hydrated sulfates in this. Looking at some of the acoustics plus LIBS chemistry data over here, this is a target called Cordoy. And in the acoustics data, so LIBS is a technique that will produce a little shock wave whenever each laser strikes the surface. And so you can use that information to get a sense of the material properties, in this case, the relative hardness between the coating and the substrate. And so you can see the change in slope at around shot 50 as we penetrate into the rock. And so you can see we're kind of delving into a softer material and then hitting a harder material. And this is the chemistry that corresponds to this acoustics data over here. And so we have the different major oxides, and you can see these trends that again start to occur between shots 25 and 50 for each of these elements. And the yellow circles indicate a compilation of the dust chemistry from some various sources. So you can see it starts off very similar, and then the composition changes as you start to analyze the substrate. So in the pixel data, this is from an abstract from Marieke Schmidt for LPSC last year. So Pixel has analyzed several purple coatings throughout the traverse. Here's an example from Cave Town. And so the coating, you can see, corresponds to this relatively mild enrichment in zinc. And so they were serving a zinc, sulfur, chlorine, basically an enrichment in volatiles. And their data indicates that it's fine grained, possibly amorphous, and it's very homogeneous, both within and across the traverse. So what about the previous missions? So Viking and Pathfinder data, it's a little bit difficult to see due to the resolution of the instruments and the capability and the limited areas that they were able to sample. So it's unclear if there were purple coatings spotted there. But for the MERS, we have some examples from Opportunity right here. You can see these various coatings, and then a few from Gusev as well. So these have been spotted in other areas, but it seems a lot more limited than in Jezero. In Jezero, they seem to be everywhere. And all these reported iron oxide component and volatile enrichment consistent with what we have with Perseverance. So some recent observations in Gale Crater, there have been several targets identified. This is some work by Bill Farron. And so you can see again in the mass cam data for this instrument, there is the strong ferric absorption again. And so these have occurred on dark tone boulder floats. And there really haven't been previous identifications. There's been a handful of new ones as well in the unreleased data, but they're very rare again compared to Jezero. So how do these form? So Janice Bishop in 2002 posited the formation of rock coatings through a process like this, where there's a deposition of windblown dust, fine soil particles, and then there's a chemical reaction with sulfate salts and or ferric phases, perhaps facilitated by clay minerals, where this gets adhered to the surface, and the source of the water could be diurnal moisture variations, frost, meltwater, etc. An alternative to this would be what Marieke proposed last year at LPSC, where the volatile enrichments and widespread natures are consistent with deposition from a vapor plume due to an eruption or degassing, etc. So here's just some conclusions. So like I said, these are widespread at Jezero, but they are far less common at the other landing sites as far as we can tell. So they could record water rock atmosphere interactions, volcanic processes. They're on eroded rock surfaces, so that could indicate a relatively young surface alteration. And so we have some outstanding questions. Why are they more common at Jezero? Was there a single event and there's more erosion at those other locations compared to where we are in Jezero? So we have a lot of work to do. We want to do a more thorough study of the existing data sets. You know, MSL has been operating for 12 years, and so we haven't gone through that completely. And compare, hopefully ChemCam on MSL will have the opportunity to analyze one of these purple coatings. So far, we haven't been able to do so. But due to the ubiquity of these purple coatings, the great news is that we have likely sampled these probably multiple times. Here's an example of this core, Montagnier, and you can see the purple coatings are spread across the surface. And so almost certainly this little core has a purple coating on it. And so there are probably multiple cores with purple coatings, and that will really help to elucidate the origin of these features.
Great, thank you. All right. So thank you all speakers for being on time, and I invite you back up to the stage for Q&A that will go for the next 20 minutes. So I invite the members of the audience to come to the mics and start grilling our speakers. Don't be shy. And when you do, please state your name and affiliation. Please.
Jonathan Lenine, JPL, and this is a question for Jiawei. So how sensitive is your alteration sequence to the chemistry of the basalt that you start with, both the chemistry and possibly the amount of water in the basalt?
That's a really great question. We actually have tested like several different like rock lithology, and then it's actually quite sensitive. And especially like if we elevate the abundance of like pelagic clays for initial profile, then we will get like much more kaolinite because it's the primary source of aluminum, right? And so the relatively decrease of iron-bearing minerals will reduce the formation of non-tranite. So that's our results. Yeah.
Okay. Good. Thank you.
Hey guys, Gwenal Caraca from University of Toulouse in France. Question for James. Really great thought, very interesting. And about, you know, I'm very fan of fans. So, especially in Carmichael crater, you show that there is a very bright band of silicate-rich material. Have you happened to find any conspicuous hints within the fan shape of particular patches that could help in doing maybe stratigraphy of differentiate any lobes rather than just a patchy distribution of the minerals?
So that the big bar of like hydrated silica, like that, I think is pretty clearly like, you know, along some kind of depositional boundary. It wasn't sort of outlined in the figure I showed, but there is also, you know, probably some faded older depositional what is it, previous depositional fan that is, you know, that actually extends past that. So I think it's pretty clear that, you know, that big bar is concentrated along a depositional boundary or layer. There are a couple other little patches where there's also hydrated silica further up in the fan, but unclear exactly if those are, you know, specific to a specific layer or something like that. Something to look into more.
Okay, thank you.
Thank you.
Hello, Matteo Loche, IRAP, France, Toulouse, as well. My question is for Jiawei. It's like kind of a dirty models questions, but basically, first, what is the software you use, the database you use for the thermochemical calculations? And
do you mean concentration?
No, it's like for example, you use for the precipitation of all your phases, you use a saturation based.
Yes, saturation.
Thing. And
yes.
what is the database you use for this?
I'm very sorry. Can you repeat that?
The database.
The
Database.
Database. Oh,
yeah.
The database is oh, I'm sorry. I cannot like specifically tell the name of that database, but like it's a database like we usually use like for the weathering simulation on Earth. So I can like show that.
I will ask you more question after.
Yeah, sure.
And just it's an important question in that kind of model. But what is the pool of phases you have for precipitation? Because you say you get non-tranite clays, but
yes.
What kind of other clays do you have in your model that can precipitate?
Okay, yeah. So we actually for our models, we the clays we input including like saponite, nantronite, and also like with different composition. Like for example, there are magnesium rich, there are also calcium rich, the clay minerals. And then we also actually put the hydrogen, the ferric hydroxide in it, because we actually at the beginning we expect that those things will form because it's really oxidizing environment, but actually no this kind of this ferric oxide is from. And also
And carbonates?
Sorry?
Carbonates?
Oh, we did not include that.
Okay,
Sorry.
okay.
Great. Thank you.
No problem.
Let me quickly interject that we can, you can ask questions of our first speaker who is virtual. The bugs have been worked out. He can hear us. So if you have questions for the first speaker, please do.
Hi, Samantha Baker, Caltech. My question also for UA about the model. I'm curious, I also noticed that I didn't think I saw that you had sulfates precipitating. I was curious, did you include sulfur at all in your model as like part of the low pH runs? Or were you considering that the low pH might have come from a different source that wasn't volcanic and therefore maybe sulfur rich?
So do you mean like sulfate precipitation in our case? Oh, so I think that's the things that we are going to like add to our models later, because for the model we are running now, that the primary source acidity is actually HCl. And actually this is not, because I mean from the observation of Martian regolith, we know that the S to chloride ratio, the sulfur to chloride ratio is around 4. So it's actually probably the majority of acidity should be come from a sulfuric acid. So I will incorporate that later to our model. So that's a reason, probably a reason why we didn't see sulfate. We actually do several sulfate run, and then we still didn't see that. And yeah, so yeah, I haven't like interpreted the data. Yeah.
Well, thank you. Look forward to seeing more.
Susanne Schwenzer, the Open University, and it's good news that we can actually ask questions of the first speaker. And I understand you had to rush this a lot, but when you talk about redox, how do you control it? What's the redox of the host rock that you are putting in there?
So if you can hear me now?
Yes, we can.
So sorry, I don't have a value in mind right now. So I encourage you to see the paper that you published a couple of months ago, because the redox states at the beginning is initiated at the beginning, and then we let the model evolve as he decide. I mean, I don't control it. He changes how he wants with the conditions. It starts with something like quite oxidant. I don't remember the value, I cannot tell you, but then it evolves as he wants with the conditions.
Okay, yeah, I wish I could ask a follow-up question in the hallway, because what I'm actually after is the redox state of your iron 2 plus iron 3 plus in your host rock that you are assuming.
Ah, okay. Sorry, no, I understand. I don't remember. Sorry. I don't
Okay,
have it in
I'll
mind.
email you.
Sorry.
Thank
Okay,
you.
Thank you.
Adam Valentinos, Brown University. Question to GOA. Nice talk. And so I have two questions. Maybe first is quicker. So you played with the range of temperatures. What happens if you go even lower? I mean, we know also liquid water freezing temperatures will go down if you have like, salts and in saline conditions. What happens in, with the precipitated phases?
Okay, so our current model, there's a issue with water. It's like the water activities cannot be like changed to like depending on temperature, because I mean, if the temperature of water is significantly lower than like freezing point, usual freezing point, if even it's very briny, the water activity will be very low, and the reaction can be totally different. So that's something that beyond the capacity of our model. Yeah.
Yeah, and so this relates to my second question.
Sure.
So did you from your results, it did not look like you precipitated out iron oxides, iron hydroxides, and we know now that there's even maybe 20% ferrhydrate in Martian dust and in soils. So are you seeing any of these in your models?
Yes, we did not see that, and I think there's several reasons of that. I think one of the possible reason is that if your fluid is reached in iron 3 and aluminum in the same time, then it will be more favorable for the production of clay. So there are multiple experiments done, like for example, they do a lot of like oxidative weathering experiments, and then most of them of single mineral like olivine, and then the major product is ferric hydroxide, and that's probably because iron is the only, there's no aluminum in the system. So I don't know if that could be the explanation. So we see a lot of iron ferric hydroxide on Mars, and then I wonder if there could be another pathway for those formation.
Yeah, because if you look at natural settings on Earth, you go to Iceland, you go to Hawaii, and
Yes.
basalts and lavas, they all red because it's so easy to leach iron and then precipitate iron hydroxides, which is usually, if it's a young deposit, it's fair hydrate.
Yes, there's a lot, and I think there's an interesting points about the relative rate of dissolution of primary mineral and oxidation of iron. So, for example, if oxidation for iron is very fast, then you will get like excess iron 3, and then it could like affect those conditions may be more favorable for ferric iron. So yeah, I'm not sure, right?
Yeah.
Hi, Joe McNeil, the Natural History Museum in London. My question's for James. I was just wondering if you had any more plans to sort of more deeply investigate specific spectral feature shapes for your hydrated silica. So I'm thinking like concavity ratio criterion and band depth ratios that can tell us about crystallinity and potential hydrothermal versus weathering origin.
Yeah, absolutely. Specifically like the lovely Cami-Shell hydrated silica deposit, Pan et al. Did a pretty in-depth study of the band ratios and quantifying the hydrated silica feature to determine, relationships between Opal A and Opal C and dehydration and stuff like that. But certainly something that I'm going to look into for some of the other deposits, which may have not been looked at so much, like the Tyrus Vallis one, where there's clear hydrated silica, but would be cool to know more.
Awesome, thank you.
Thank you.
Hi, Kaushik Mitra, University of Texas, San Antonio. So my question is for Jave. Did you include kinetics in your study, or it was just thermodynamics?
We include kinetics, so the whole system is time dependent. So we actually can generate a series of time of the profile. Yeah.
All right, thank you so much.
Okay, and also thanks for this, because I have read so many articles from you, and then it's really thanks for your pioneering work in this field. Yeah, thanks.
Sorry you had to read all my papers.
No.
Okay, 1 second. I'm going to take chair's prerogative. I want to ask a question about coatings, because those coatings are really cool. So they strike me as being fairly friable, that they can be sort of chipped off, in fact, flaking away, which isn't like most terrestrial rock coatings that I'm familiar with. Do you have a sense of that and what that might be telling us?
Yeah, so I think you're right that they do seem like they are chippable, but I don't think that they are super soft. I know in that acoustics profile there that was softer than the underlying substrate, but that was that particular substrate. We did another one on the deltaic material where it was the opposite trend, where the coating was harder than that particular material. And so while I think they are chippable, I don't think they are you can't peel them off. So it's kind of both are the same thing. Like they are very brittle, but they aren't, they're very well adhered to the substrate in most cases, it seems like. So that is kind of like the ones that you see on Earth.
I also had a question regarding the coatings. So do you ever see a coating like on top of another coating? Were there multiple episodes of coating emplacement, or was it just like one discrete event?
And there was one case where it did look like there was a couple of layers in the coatings, and that would be consistent with terrestrial coatings as well, which tend to form in layers at different periods of time. So it's difficult to say with the data we have available. That will be great to have those cores back that have the coating on the surface. But I suspect that there is layers within the layers for at least some of these materials. We haven't seen mixed coatings yet. That's something that you do get on Earth, where you can have sort of a silica-rich layer alternating with a sulfate-rich layer, for example, in Antarctica. But we don't have the resolution to see that with our instrumentation, but it is a possibility.
Thank you.
This is Haru Tabata from JAXA. I also had a similar question to coating, those purple coatings. So like you showed that those coatings vanishes after like 25 to 50 laser shots. Could you tell us like what would be the thickness of such coatings, and do you have a I mean, is those coating thickness? Does those thickness imply something about the formation mechanism?
Yeah, so as far as our depth profiles are concerned, the rate at which we excavate with each laser pulse depends on the hardness of the material. And, we're just guessing for on Mars. We have some data in some of our papers from terrestrial basalts and dolomites and things like that to get a depth. I would guesstimate, usually when we are shooting a rock on Earth, we would start to penetrate a coating that's 10 to 50 microns thick after about 15 to 50 shots. And so this would be consistent with that. We have seen places on Mars where there's definitely a visual coating, but we do not see a change in depth. And so in those cases, they're probably more on the order of 100 microns thick or thicker. Those ones that we looked at, could be a millimeter or two thick. And so in certain cases, we can get a sense for the thickness of the coating in that case. And I forget the second part if there was a...
Well, I didn't realize that there was like variations in the thickness, but I just thought like if we know the thickness, that could help constrain the formation mechanism. But
I would say not really, just because we don't know what level of erosion, what part of the erosional phase we're at, or depositional phase. I don't really think we're in a depositional phase. I think we're in erosional phase across the planet here. So we've seen some very thin that are super wispy coatings, and then we've seen thicker ones. And so I think it depended, on the formation environment. If it was in a divot or in a hole, it likely got thicker than on the other regions, and then it's been eroding in certain areas preferentially versus others. So not really, I don't think.
Phil McCausland, University of Western Ontario, and I have there's lots of coding questions right at the end, so I'm going to ask another coding question. And this one is just about, are you doing or are you aware of kind of a systematic spatial assessment of the coatings of rocks, in the sense of trying to assess, okay, how did they possibly form? Is there prevailing wind kind of correlation with that? And are there regions of Mars where that would be different? And,
Yeah, that's something Brad and I have talked about. We haven't really done a detailed assessment of orientation of the rocks that it's on, or regional, like is it windier in those other areas? And so therefore there's been more erosion. And so that's why we see them less frequently elsewhere, or things like that. So that's something we sort of have planned if we can find the time.
Yeah. How long does it take to make a coating?
Yeah.
Well,
I mean,
okay.
on Earth, they've tried to do studies like this to see where they've scraped off coatings, and this has mostly been done with the rock varnish, the manganese ones. And so some of those can happen very fast, but usually those are the ones that are biologically mediated, because life will infiltrate and, produce very quickly. An abiotic rock coating, it really depends on the environment, the specific conditions. So there's not a clear, could be millions of years, could be hundreds of years.
Or whether it's a very long-term thing may help distinguish between the formation mechanisms that are proposed.
Yeah, that's true.
Okay.
All right. I'm afraid I'm going to have to cut this off and thank our speakers. And next up. So next up is Rachel Shepard with a talk entitled "The Presence of Magnesium Sulfate Can Obscure Spectral Evidence of Siderite." Oh, this is a virtual. Okay. Rachel, can you hear us?
I can hear you. Can you hear me?
Yes, we can. So why don't you start talking, and your slides will be up momentarily.
Okay. Is this volume all right?
Sounds good.
Okay, great. Thank you so much for the introduction. So can you advance the slide, please? You'll steer, right?
Yes.
There it is. Okay, great. So carbonates most commonly precipitate from water, and their specific mineralogical type is a valuable record that can constrain fluid composition. And so cataloging their type and extent on the Martian surface is important for understanding the planet's history and water budget as a whole. And furthermore, modeling of ancient Martian surface waters in contact with the CO2-rich atmosphere suggests that carbonates should have formed in large quantities during the Noachian, especially the iron carbonate siderite, which is the most insoluble major common carbonate and should precipitate first under early Mars conditions. And while they have been detected in a range of meteorites and Martian dust, carbonates detection via orbital spectroscopy on Mars has been limited, despite having clear spectral signatures, which you can see here on the left. In part, this may be due to overlapping absorptions, Martian dust, and instrumental detection limits, but in theory, carbonate spectral features should be visible at around 1 volume percent. So why did widespread carbonates form and were destroyed by acidic groundwaters or volcanic gases? Could they possibly be obscured from orbital spectroscopy, which is only sensitive to the upper tens of micrometers of the surface? Or did they never form, either due to acidic surface water, low atmospheric PCO2, atmospheric escape, or aqueous processes occurring in the subsurface out of contact with the CO2-rich atmosphere? Next slide, please. Unlike carbonates, sulfates have been successfully detected across the Martian surface, both from orbit and in situ, with their widespread coverage forming the foundation for our canonical understanding of the Hesperian. They also come in many mineralogical forms, both in terms of the cation, but also an enormously changeable number of structural water, which can attach to the sulfate crystal structure. And the number of structural waters affects the reflected spectra, because it requires a restructuring to fit them in, changing the bonding environment. In addition, in the case of magnesium sulfate, which is very common on Mars, exposure to a dry Martian environment is enough to remove structural waters through time and cause changes to the spectra, as you can see here on the left, where exposure to just a few hours of current Mars surface humidity changes this initial epsomite spectrum with 7 waters on the bottom in black to an X-ray amorphous sulfate with 2 structural waters, which is the top spectrum. And the main spectral features to note here for sulfate are the 1.4 and 1.9 micron water absorptions, which decrease in both depth and width as the sulfate loses water. And there's also a characteristic drop in reflectance beyond about 2.2 microns that leads to this convex shape that is typical of sulfates. So these sulfate absorptions are quite strong, and magnesium sulfates are quite common on Mars, including Gale Crater, and they strongly absorb in some of the same regions as some of carbonate's characteristic absorptions. Next slide, please. And so if we look at the orbital spectra along the Curiosity traverse route in Gale Crater, I would draw your attention here to the solid pink and the hashed pink areas, which all have spectral evidence of magnesium sulfate. And they have been seen in situ as well. The Kevin XRD instrument on Curiosity has observed both Starkeyite, which has 4 structural waters, and Kieserite, which has 1 structural water in Gale Crater. And somewhat surprisingly, carbonate has also been observed in situ. So each dot here along the traverse route is a drill target where the underlying target names contained iron carbonate in the in situ XRD data. Most notably, that includes Topo Caparo, which is labeled TC here, which had 10.5 weight percent siderite. But even though we know carbonate is spectrally distinct and it's confirmed in the bedrock here at over 10 weight percent abundance, which should be visible, we still cannot resolve it in orbital data. And because of the proximity of magnesium sulfate and carbonate bearing materials in samples analyzed along the traverse, we sought to identify whether the SO4 and the H2O related features in magnesium sulfate spectra may be masking the presence of iron carbonate in these visible to near infrared wavelengths when the 2 minerals are intimately mixed as they appear to be in this part of the sulfate bearing unit. Next slide, please. We physically mixed siderite and epsomite grains in 5 different ratios and collected spectral images at 3 time points, which were 0 hours, 3 hours, and 1 month. And this allows us to test the effects of exposure to the N2 purged dry chamber environment that houses the micro and mega imaging spectrometer at IAS in France. And with this method, we want to track how the presence of different magnesium sulfate hydration states affects the visibility of the carbonate absorptions. And so on the right, you can see the starting FTIR spectra of both mineral components separately at lab conditions. And the magnesium sulfate is in pink with these strong 1.4 and 1.9 absorptions. and this low reflectance beyond 2.2. And it's epsomite at lab conditions here, but it's going to lose water and crystallinity as time passes in the dry chamber. And then the siderite spectrum is in green. And note that although the carbonate overtones at 3.45 and 3.9 have greater band depth than those at 2.3 and 2.5, their use is somewhat limited due to the susceptibility of these longer wavelengths to artifacts in both CRISM and omega orbital data. And so much of the focus in identifying surface carbonates now is on the 2.3 and 2.5. So that's what we will be focusing on with micro omega. Next slide, please. So here is our result 1. Each micro omega image here is a 5 by 5 millimeter coverage of one of the 5 physical mixtures, and then each pixel contains a reflectance spectrum. And so here the images are color-coded with S index in red and blue, so that strong sulfate signatures are pink, and then we have min 2345, 2537 in green, so that iron carbonates are in green. And then X in this big plot is the mineral axis with increasing carbonate ratios to the right. And then Y is the time axis showing you 0 hours, 3 hours, and 1 month of this dehydration. And if we look at the micro omega spectra of the individual sulfate grains on the right, we can see that as the sulfate component dehydrates through time, it is going from 7 to 4 to 2 structural waters. So this gives us a baseline of what the time dimension is doing. Next slide, please. Result 2 is that even in 75% carbonate sample, the 2.3 micron absorption is obscured at the scale of a micro omega image. And so on the left, I'm showing you which images we're pulling from to keep you oriented. So these are very carbonate-rich mixtures that we're showing here. And then in the middle, you can see spectra from the 3 different time points. And within each panel, the green spectrum is a 5 by 5 pixel average over just a siderite grain, where you can see the 2.3 and 2.5 that are characteristic of carbonate. But then if you average over the whole image, which is the black spectrum, the 2.3 micron feature is not visible at all, just the 2.5. And this is really important because, as discussed before, a lot of our methods to look for carbonates on Mars, like spectral parameters, including min 2345, they focus on looking for both the 2.3 and 2.5. But we're seeing that the 2.3 can be pretty easily obscured in the presence of sulfate, which is widespread on Mars and co-occurs with carbonate in Gale.
Next 2 minutes, Rachel.
Okay.
2 minutes.
Finally, we have result 3. So even at the 5 by 5 pixel scale, the carbonate grains have sulfate-like features in the presence of more hydrated, more crystalline sulfate. And so as shown on the left, these are spectra pulled from mixtures with 25% carbonate, and the pink spectra are spectra over the individual sulfate grains within those mixtures, and the green spectra are over individual carbonate grains in those mixtures. And so the right 2 panes, T1 and T2, those green spectra have a 2.5, sometimes a 2.3, they look like carbonate. But at T0, even if you're taking pixels only from the siderite grain, they're being contaminated with sulfate features from the epsomite. It would be hard to identify those as carbonate. And so even at this scale, much finer than can be achieved from orbit, if the sulfate is sufficiently hydrated and crystalline, it is affecting the spectra of the individual carbonate grains. Next slide, please. So that leads to a recommendation where possible to focus on identifying carbonates on Mars with the 2.5 rather than necessarily the combination of 2.3 and 2.5. The effect of focusing on just the 2.5 is demonstrated here, where the left is our original image that's using min 2345, 2537, which is looking for both bands. And then on the right, we have a version that's just looking at the band depth of 2.5, and you can see the response of the siderite grains is much stronger, and we're pulling out more grain texture within the mixture. And as sulfate is one of the most common secondary minerals on Mars, this is affecting many orbital images that could possibly be re-examined. And care should, of course, be taken when looking for a 2.5 that it's sharp and distinct and not a broader feature or a shoulder that could be caused by some other clay minerals or other sulfates. Next slide, please. My final slide is just that this is important because the locations that we know siderite exists in Gale, which are the underlying drill targets, are all in these sulfate-bearing areas, and they all have these orbitally invisible carbonates at up to 10 weight%. And so our finding that polyhydrated magnesium sulfate may obscure carbonate detections is both consistent with that observation by Curiosity and has important implications for early Mars and these minerals that can act as both water sinks and have implications for the planet's aqueous and atmospheric history. So you can go to the next slide. It just says, thank you so much for your attention, and I look forward to discussing more. Thank you.
Thank you, Rachel. Please stay around for the questions. If
Okay.
you can. All right, next up is it is Changqing Wang, and it's the presence of magnesium sulfate moving on. Effects of protolith composition and advection on ancient Martian carbonates. Take it away.
Okay, good afternoon. I'm Changqing Wang, a PhD student at the University of Tokyo, and I'll present our study on the formation of ancient Martian carbonates. How do I go to the next slide? Oh, okay, thank you. So carbonates have been a focus for many missions to Mars, and this map on the slide shows a summary of all the carbonate detections on the Martian surface to date. And the carbonates can be divided into two categories based on composition, including magnesium-rich carbonates, which are the green dots, and calcium iron-rich carbonates, which are the orange dots. So the presence of two different kinds of carbonate compositions suggests at least two sets of different formation conditions for carbonates. And since calcium iron carbonates appear to be associated with more felsic rock compositions on the Martian surface on a global scale, it is possible that protolith composition may be a reason for the different carbonate compositions, although other environmental factors may also have been responsible. Also, given the evidence for liquid water on ancient Mars, conditions suitable for carbonate formation by low-temperature water rock interactions were possibly widespread on ancient Mars. And in many of these environments, effective transport may have played an important role, such as in groundwater systems. So the aim of our study is to understand the effects of protolith composition and effective transport on ancient Martian carbonates. So to achieve our aim, we conducted thermochemical simulations. Our simulated geological setting is alteration by groundwater in contact with a 1 bar carbon dioxide atmosphere. And depending on the fluid transport process, it can represent a standing groundwater environment under a body of water, or the infiltration of groundwater during a period with melting and or precipitation on Mars. The temperature was fixed at 5 degrees Celsius, and initial water-to-rock ratio was 5/50 by mass. And we tested the list of variables listed on this slide. For protolith composition, we included a mafic and a felsic protolith composition. Both were derived from rover measurements. And it should be noted here that we use the term felsic in a relative sense without consideration of a threshold for silica content. For fluid transport, we included diffusive, which was diffusion only, and advected dispersive, which included downward advection. For the duration of alteration, we had a short duration of around 3.2 Earth years and a long duration of 100,000 Earth years. The simulations were conducted in the Freak software with the crust represented by a series of cells, each containing 1 kilogram of pure water and some protolith phases. And kinetics were considered by suppressing high temperature phases and including the dissolution rates for protolith phases. Now let's look at the results, starting from the mafic protolith with the short duration of alteration. So the figure on the left shows the vertical profile of mineralogy. Of the protolith phases, anorthite and magnetite were substantially dissolved, but other phases only had limited dissolution. The figure on the right shows the carbonate composition, and they were predominantly calcium iron-rich carbonates, and the carbonates were mostly associated with aluminum or iron phyllosilicates. Next, we look at the mafic protolith with a long duration of alteration. The protolith was almost completely dissolved, and the resulting carbonate composition was mostly magnesium iron carbonate with some calcium content. And there was a evolution of carbonate composition from calcite to huntite and then gradually replaced by siderite. And the associated secondary silicates included magnesium iron phyllosilicates, amorphous silica, and zeolites. Next, we look at the felsic protolith, starting with the short duration of alteration. After the protolith phases, anorthite completely dissolved, and there was limited dissolution for other protolith phases. And the resulting carbonate composition was pure calcium carbonate, and they're associated mostly with aluminum phyllosilicates. And finally, we look at the felsic protolith with the long duration of alteration. The protolith was substantially dissolved, except for quartz and also pyrite, which did not dissolve. And the resulting carbonate was calcium iron rich with no magnesium content. A wide variety of phyllosilicates were produced, and many of them contain interlayer potassium ions. Also produced were a large amount of zeolite minerals. So combining the results above, we show that protolith composition and duration of alteration can control the composition of carbonates and secondary silicates. So starting with the two different protolith compositions, felsic and mafic, each with either short or long duration of alteration. Together, these two factors control the types and amounts of protolith minerals dissolved in a fluid, which affects the fluid composition. And the fluid composition in turn determines the carbonate and secondary silicate compositions. We found that under a low temperature and a steady carbon dioxide atmosphere, large amounts of magnesium carbonates can only be produced by a mafic protolith with a sufficiently long duration of alteration. We also found that calcium iron carbonates that are not associated with olivine are likely the result of a more felsic protolith. Next, we did some preliminary comparison of our results with rover observations in two sites on Mars with possible low temperature lacustrine environments similar to our simulated settings. And these are Zeta Formation in Jezero Crater and the Glen Torridon region in Gale Crater. We interpret the Zeta Formation as a mafic protolith with a long duration of alteration, and the Glen Torridon region as a more felsic protolith, also with a long duration of alteration. Our interpretations are consistent with observation for carbonate compositions, the igneous compositions, and some aspects of the secondary composition. But there were some inconsistencies. For the Zeta Formation, our simulations produce mostly iron 2 plus phyllosilicates instead of the iron 3 plus phyllosilicates detected by the rover. And this may be explained by the lack of oxidants in our simulations. Also, Zeta Formation contains well-preserved olivine, and the amount of carbonates is low compared to the complete dissolution of our protolith in our simulation. And this can be explained by the protoliths in our simulations representing only the parts that actually interacted with water instead of the whole rock. For the Glen Torridon region, nontronites are common, but they were not produced in large quantities in our simulations. Other than the lack of oxidants, the low iron content of our felsic protoliths may also be a reason. So an external iron source, such as lake water or dust, may be needed for the formation of nontronites. Also, our simulation produced a large amount of zeolite minerals, but zeolites have not been detected in the Glen Torridon region. And next, we look at the effects of advection on carbonate formation. So by comparing different simulation cases with diffusive transport and advective dispersive transport, while other variables are kept constant, we can see that advection greatly increases the efficiency of carbonate production, with the advective dispersive case shown on this slide producing 2 orders of magnitude more carbonates than the diffusive only case. And we also found that advection can cause the production of underground carbonates by causing redissolution of surface carbonates and also accelerating the downward transport of dissolved carbon dioxide to precipitate carbonates deeper down in the crust. So in conclusion, we conducted thermochemical simulations to test the effects of protolith composition, fluid transport, and duration of alteration on carbonate formation in a possible ancient Martian environment with low temperature and a state carbon dioxide atmosphere. And we show that protolith composition and duration of alteration can control the compositions of carbonates and other secondary minerals. We found that magnesium carbonates can only form from a mafic protolith and likely requiring at least a few thousand years of alteration by liquid water. Also, calcium iron rich carbonates that are not associated with olivine were likely formed from a more felsic protolith. And for the effect of advection, we found that advection affects the amount and distribution of carbonates by greatly increasing the efficiency of carbonate formation and also providing a mechanism for the formation of deep underground carbonates on Mars. So this is the end of my presentation. Thank you for listening.
Up next, we have William Rapin presenting siderite-rich laminae at the marker band contact in Gale Crater.
Thank you. Hey everyone, so I'm going to tell you in this talk about some exciting recent data about carbonates from Gale Crater. Here you see the main culprit is from a lamina, and so spoiler, this is about this outcrop, and some of those small fragments help highlight this very new and specific lithology and chemistry we've seen here. First, there's been a lot introduced about carbonates already. This is a global map of alteration mineral that's fairly recent and has been pointed out. Carbonates only are observable on a few locations. It's a long-standing research, this looking for those carbonates on Mars. It's an important mineral, of course. We would expect that to form under CO2 atmosphere under the right condition. On Earth, we know carbonates is really a driver for the long-term carbon cycle. So we really need to look at those Martian carbonates to understand what happened on that planet early on. And unfortunately, so far it's been really hard to make sense of how they form. Namely, the environment that's associated to them has been elusive. And it turns out that curiosity at Gale Crater has a lot to offer on carbonates, actually. So you've probably heard of that. That's been told in the past couple of years. That we've came across the marker band. We've been tracking that band from orbit for a long time, and so now we've gone through it. We did a campaign there, and when we drilled just above the marker band, it's almost part of the stratigraphy here. That's where we identified using X-ray diffraction 10 weight% siderite in the bulk of that sedimentary rock here. We went onto that actual resistant feature here. Unfortunately, it was a little too hard for drilling, although we have lots of chemical data there from APXS and ChemCam. And what came out from that marker band that I want to mention here is that here the depositional environment is really clear. You've seen that talk from Claire Mondro about those wave ripples indicating deposition in the shallow lake. They form from the action of waves from the wind. And so they are fossilized there. The whole strata really is a testament to that lake existing at that time and grading here. And in terms of composition, this is the chemical data we were able to drive. This is from APXS reviewed. So the bulk of those targets really show that nice in red here enrichment in iron, quite high, above 35%, and in zinc and manganese. So there is something standing out here. What we wanted to try here on the study is look at also at ChemCam data and see, because ChemCam is sensitive to light elements like carbon, and see could we find. So we tried that. Something warning is that carbon is really hard to detect with ChemCam laser-induced breakdown spectroscopy on Mars in particular, because carbon, when we produce the plasma from the laser, it forms a plume in the atmosphere which excites the atmosphere itself. The atmosphere is CO2, so there is a carbon coming from the atmosphere that is acting as a noise. So understanding if the carbon comes from the target or the atmosphere is really tricky. We tested that in the lab. This is paper recently published, right in time. We got lucky on that. By Pierre Beck. Here you see carbon and oxygen. So you see the two go together on carbon-free sample. But when we shoot at carbonates, you see that some pure carbonates can have a distinguishable signal. But if there is only 25, you see it's barely significant. What came out of that paper is that if you see a carbon signal from a carbonate that mixes in a silicate, it means that there is at least 50% by weight of carbonate is being tested for calcium, magnesium, and iron carbonates here. And so when we applied this methodology to the data accuracy, so when that paper was published, we didn't go to the marker bed yet, but so we had the paper said, oh, we didn't detect any carbonate, but then we arrived to the marker band, and this is how the data plots. You see, iron has a function of elevation, and this is carbon signal. That's the very noisy signal. And when you put those both, see here, you see really the marker band stands out compared to that host stratigraphy in terms of iron that's expected from APXS. But here, what you see here, there is a slight trend of the bulk marker band data, positive carbon and iron. This is barely statistically significant, unfortunately, but there is one target we're going to talk about in that talk a lot is Mapiripana. So it's hard to pronounce, sorry, but we're going to have to pronounce it because it's key to this talk. And this one, as you see, it's important for two reasons. It's the most enriched in iron target that we've seen with ChemCam. You see some points here in gray that are from sporadic detection of iron oxide at the millimeter scale. This target, the whole 5 points, are enriched in iron and in a homogeneous manner. So it's a pretty homogeneous target at the millimeter scale. And it's the most enriched. And it has also, secondly, a positive carbon detection, which directly places us above 50% carbonate in that rock. So the bulk of that rock is considerably enriched in iron and carbonate. And that's why we infer this is a siderite-rich target. So what does it look like? This is the phase shift of that target. Histologically, you see this, the analysis was done on the plane, this planar surface here, that actually is pervasive to that block around. There is an assemblage that's typical. It's always surrounded by nodules that are on the lamina above. And the lamina itself is maybe composed of several laminae. Here you see them exposed here as well. And possibly a couple laminae are in this profile, this lithofacies. We've seen it also outcropping in the marker itself. And so the question really came with this is really a single target. And so we are, this facies really looks identifiable. We're going to look at facies at the marker band to see how we can track it. So we mapped all of the facies of the marker band in a level of detail that's adequate to differentiate this target from the others. Really, this target stands out. It's here. It's really unique. It has this association to nodules, but the target is actually on the lamina. And all the others, lithofacies type, are not enriched in carbonate. They are lower in iron. And they are also quite diverse, but they are really distinct. Unfortunately, APXS did not sample that, only ChemCam. And we sampled only once at Mapiripana. And so to give you more example, this is what we tracked. We tracked all the images, seeing if we had seen that culprit around. And you can see the outcropping. This is how the marker band shows in some images. You can see that there is this contact here. It's hard to find a proper contact to elucidate. And also the view is side on, but the target itself was shot from above. So luckily, we have those fragments that have the same view angle to positively identify that facies, but we need to go back to the actual in-place bedrock. Sometimes it's available. Here you can see here the planar bed, and here those fragments that show those laminae stacked and some nodules on top. You can see here again a lot of fragments. It's actually everywhere on that facies. Thanks. And this is one of the largest blocks. So you see really it's a facies that's part of that strata. And so this is the overview. You see where we've seen this target, this type, we call that Mapiripana type. It's a platy silty laminar that's really draping the bottom of the contact. Anywhere we could see the contact, that's where we've seen it. Where we hadn't seen it, it was because contact was not available, actually. And so it's at the base, really the transition into just below the wavy ripples facies that's here. That's typical of the shallow lake. And one important observation is that Mapiripana is seen in an irregular geometry, both at meter scale and decameter scale. And every time we spot it, it's always the same thickness, millimeter scale lamina above nodules. This is typical of a geometry of a lacustrine deposit that drapes above. It also has this silty texture. And it's also a chemical deposit. It's so enriched in siderite. And so all this makes it a phase that's consistent with a lacustrine deposit, a chemical lacustrine deposit. So because we think now with that deposit, we can model the whole river lake system that is in interaction with the atmosphere. And honestly, we haven't run the model yet, so sorry. We haven't used so far, but the model is ready. It's an effort ongoing right now by Matteo Losch. You will see his presentation on Thursday, and please have a look at it and come and help us understand that target. And what I mentioned here to summarize, really this is the first detection of siderite by ChemCam, and it's not the least because when we see it, we really see a lot. And it's the most siderite-rich strata, really. And it's at a location we can really constrain the environment, the paleo environment there. It's a lake. So we think that from this coupled river lake atmosphere, we can use it as a chemical marker of the evolution. We are, then wave ripple with mostly hematite below siderite and below another. So there is a complex evolution that we can fully characterize there using that model and put additional constraints. So yes, please come talk with us if you're interested in that. And thank you for your attention.
Next, we will have a virtual talk from Anushri Srivastava, talking about in situ observations of hydrated carbonate in Jezero crater, Mars.
Can you hear me okay? Can you hear me okay?
The audio is not coming in great.
Volume is very low.
Your volume is very low, your input volume. Get a little closer to the mic or...
Can you hear me now?
Still quiet.
Still pretty quiet. Anything we can do in here, or maybe go to your input settings on Zoom?
I've done that already.
Okay, it's much better.
Yeah, okay. Yeah, so hi everyone, I'm Anushri and I'm a postdoc at Carnegie Science in Washington, DC, and I'm also a postdoc collaborator for Mars 2020 mission and the Sherlock team. So I'm going to talk about the in situ observation of hydration in Martian carbonates. So next slide, please. So a high-level summary of this presentation. The orbital investigations identified the margin of Jezero crater as rich in olivine and carbonate deposits, mainly along the inner margin of the crater, making it a significant geological feature in terms of its history of aqueous alteration and potential for any past habitability. The Raman spectroscopy on board Perseverance rover as part of the Sherlock instrument performed its first ever in situ detection of hydration in carbonates on the surface of Mars. And this hydration feature in Martian carbonates was further identified as a mineral called nescohonite, which is magnesium carbonate trihydrate, which is detected on Mars for the first time, both orbital and in situ. However, nescohonite has a narrow stability field. So the big question here is how this metastable mineral has been preserved and hydrated for such a long period of time. And we are trying to discuss several ideas and possibilities in the paper that's under review. So stay tuned. Next slide, please. So the Mars 2020 Perseverance rover landed in Jezero crater in February 2021, and Jezero crater were basically chosen for the landing site because of its evidence of an ancient lake bed and with a prominent river delta, indicating a possible habitable environment that could have supported ancient microbial life. So here is a cartoon of the rover, and what I'm indicating in a box here is an arm-mounted Sherlock instrument, which stands for Scanning Habitable Environments with Raman and Luminescence Organics and Chemicals. And it is one of the 7 science payloads on board the rover. So the instrument has 2 main components, Sherlock Raman spectroscopy and Sherlock Watson, that is a color camera used for taking close-up images of grains and rock textures. Sherlock uses deep UV resonance Raman and fluorescence spectrometer, utilizing 248.6 nanometer deep UV laser and less than 100 micron spot size. So these are the set of goals to examine history and habitability of potential of Jezero crater, to examine the availability of key ingredients of life as we know it, to determine the preservation of biosignatures in ancient Martian substrates, and to conduct analyses of minerals and organics for the future sample return mission. Next slide, please. So here's an enlarged view of Jezero crater and the fan delta that is primarily located within the western margin of the crater basin. So what is highlighted here in the red is the distribution of hydrous and anhydrous carbonates within the margin unit, and that is next to the fan delta, potentially indicating a past lake environment where these carbonates deposited over time via carbonation. So studying these carbonates could provide some useful information about Mars's ancient climatic conditions and their potential to preserve any biosignatures. And the location with the star here is the geological unit, or workspace as we call it, where the first abrasion operation in the margin unit was conducted. Next slide, please. So the first abrasion of the margin unit was called Amherst Point in the Hans Amundsen Memorial Workspace. And when we expand the workspace bedrock, we see a vein on which the Amherst Point abrasion patch was laid out. The patch is of around 5 centimeter diameter and of around 0.7 to 1 centimeter deep. So talking about the textural features of this workspace, it is fractured into irregular polygons, and the surface is like typically dusty and also show a linear feature cross-cutting the bedrock, which we inferred as mineralized vein, as we see here, showing a kind of post-depositional fluid rock interaction. Since the abrasion patch here lacks a kind of interlocking texture of grains that is common to igneous rocks, so it is classified as sedimentary rock, and it contains a variety of grain types that would suggest a kind of aqueously altered sandstone. So the Pixel instrument, which is actually the in situ XRF capability on board the rover, so laid out a 2 pixel scans of by 5 by 7 millimeter, 2 Sherlock survey scans of 5 by 5 millimeters, and 4 Sherlock detail scans of 1 by 1 millimeters across 2 sols. And here is the Sol 920 detail 1 scan that I'm going to talk about in this presentation that is placed on the colorized microscopic image. Yeah, so next slide, please. So here is the Sol 921 detail scan Sherlock observation results. And here we see 7 points highlighted where hydrated carbonate has been detected. So as we see in the spectra, the V1 peak occurs at around 1090 wave number, and hydration band or OH stretching band shows up around 3500 wave number. And these features are characteristic to hydrated carbonates. Next slide, please. Now, when we align and compare the 7 Sherlock spectra with various types of hydrated carbonates in the rough database, lab synthesized nescohonite, and the nescohonite spectra that we obtained from our Sherlock analog brass-bore instrument, so that's bingo, like we found the best match is with nescohonite compared to the similar hydrated carbonates such as artenite, dipingite, and hydromagnesite. We also verified the mineral composition with Pixel. Pixel results of the Amherst Point by co-registering Pixel and Sherlock detail maps of the abrasion. So Pixel calculated weight % of magnesium iron in that region, and also inferred the distribution of carbonates in those points that I'm showing here. So that is also somehow masked by the presence of magnesium iron sulfates that I'll talk about next. So next slide, please. So not only hydrated carbonates, but Sherlock also detected associated hydrated sulfate in the abrasion. And as I show here, these 4 points in the Sherlock detail 1 scan dominated by the presence of hydrated carbonate associated with hydrated sulfate at around 1020 wave numbers. Next slide, please. So to identify what type of hydrated sulfate that we see here, we compared the fitted wave numbers in Sherlock data with various sulfate peak center and hydrated bands in the literature. And we found out that it matches nicely with magnesium sulfate trihydrate. So out of many hydrated magnesium sulfate species, we shortlisted 3: dihydrate, trihydrate, and tetrahydrate. And based on V1 peak center, as we see in this little table here, dihydrate was too high and tetrahydrate was too low. So we concluded that it should be trihydrate, which was like a closest match, and also consistent with previous finding in the delta top studies. We did not really compare the hydration band because a wave number shift is kind of something we expected because sulfate hydration is co-occurring with carbonate hydration. And talking about that, in that figure on the right, we found that when sulfate is present, the intensities of hydration bands are higher, and when sulfate is compared to when sulfate is absent. So indicating that clearly indicates that sulfate is hydrated. Also, intensity of OH band is not correlated with sulfate V1 intensity, indicated that these two components kind of contribute to the hydration of carbonates and sulfates. Next slide, please. So what it really means for a Lee Mars, experiments have demonstrated that the dissolution of olivine and precipitation of nescohonite and amorphous silica occurs via carbonation reaction that I'm showing here. So we expect a kind of similar process for nescohonite formation on Mars, possibly, given Sherlock and pixel scans of Amherst Point identified a kind of plastic sedimentary unit with deposition of nescohonite, sulfate, amorphous silica, and primary silicates, suggesting kind of formation via aqueous alteration. Also, the spatial association of these minerals that I just mentioned indicates that alteration of igneous materials that is consistent with the interpretation of Jezero margin, as we've seen papers before. That is possibly a fluvio-lacustrine environment. And such an aqueous environment would have been persistent for a prolonged period of time under low to moderate temperatures, pressures, and alkalinity to prevent nescohonite transformation into its less hydrated forms. This also provides. I'm just finishing. So this also provides a critical concern to past Clement conditions within the margin unit, both the formation and long-term stability of nescohonite and possibly maybe early habitability. Next slide, please.
And we have to move on. Thank you.
Okay.
And now if our 4 speakers or 2 in-person speakers and virtual speakers can remain online and come up to the stage and answer some questions. We'll be taking questions in person. Please line up at the mics and also virtually. Thank you.
Kate is on? Yes, I think. Kate Hendrickson, Rutgers University. I have a question for Dr. Shepard, if you can hear me.
I can hear you. I'm here.
Okay, great. Really great work, by the way. I anticipate that will be highly cited and is going to really help us with a lot of analyses looking for carbonates. I did have a question, though. With such a, I don't want to say simple, I guess, but with this new band parameter looking at just 2.5, how worried should we be about false positives for other things that are not carbonates being detected by that band parameter?
100%. I think that's what really needs to be focused on when we're encouraging people to look for just the 2.5 and not the 2.3 and the 2.5, because other things can absorb in that area. And so it'll have to be compared like with the carbonate spectra and the spectra of the mixtures that we're presenting, and then compared really carefully against other clays and sulfates. Luckily, a lot of things that absorb in the 2.5 tend to be quite a bit broader, or these sort of shoulders, as I was describing, but it's definitely something to be treated with a lot of caution. And so I wouldn't necessarily recommend like making a band depth map of the 2.5 all across Mars and then saying maybe these are all carbonate detections. But I think as we're doing really careful spectral mapping, looking for some of these phases that have been largely eluding us for a long time, it's something to keep in mind. In some previous works, it's been noted, oh, this area has carbonate-like features, but it's missing the diagnostic 2.3, and so we're not going to call it carbonate. We're trying to get that to be something to keep in the back of your mind as you're starting to look for those features.
Okay, thank you.
Thanks.
This is Janice Bishop
from the SETI Institute, and I wanted to ask Rapine and some of the Gale team, what do you think in light of Rachel's work? And this siderite is this tiny little deposit in one area, but there's kind of a lot of it. So what if there's a little bit of siderite in other places, but it wasn't found yet? Can you use Rachel's work to go back and look? And are you hopeful that there's more, or do you really feel that the siderite's only there in that one site?
Yeah, I think Rachel's work is also, yeah, it's indeed very important to understand the observation bias. There is this massive sulfate unit that we call now the carbonate unit even. It has siderite at a level of significant, 10 weight percent or so. The one we've identified that I've talked about is really that laminae, and it's siderite rich to a point that is has been never seen so far, but it's obscured by how it's exposed. This one is really obscured because of its outcropping at the base of an outcrop that is resistant and above it. So I don't think it leaves a lot of luck to see it from orbit. But that'd be, yeah, I don't know if Rachel can comment on the scale of heterogeneity, but that's because it's true that this lamina, where exposed, it's mostly siderite, but it's only very partially exposed. You've seen the fragments and how, so that's a scale of exposure that is, I know Rachel tested mixture down to millimeter scale. If we have mixture, but with a coarseness of centimeters or decimeter, I don't know how it shows up. That's a question for spectroscopists.
Probably not 18 meters from Prism, but maybe from the VisIR on Chem.
Oh yeah, we haven't seen it with the VisIR. The
Okay.
CDI doesn't show up.
Okay,
Yeah.
all right, thank you.
Hi, this is Jiawei Wang from Cornell University, and I have two questions for another Mr. Wang. And the first one is, I would really like to know, what's the iron bearing phase, for your model in the fail-sick setting?
You mean the iron bearing file?
Mineral in your fail-sick, yeah.
For the fail-sick setting, I don't have my slides here. I'll have to try to remember what.
I remember you got andesite, but yeah. So what's the iron bearing phase? Is it
I think
biotite, hornblende, or what?
I think for the fail-sick case is the irons in siderite in the
siderite.
upper part of the column, and then below it there's I think saponite, the iron bearing type of saponite, I think.
Oh, so you start with saponite and some siderite, is that?
I didn't start with saponite. It was part of the secondary mineralogy.
Oh, so yeah, so where the originally
Oh, you mean
yes,
where was the iron?
yeah, in the leaf of
in the protolith.
yeah, protolith, yeah.
So for the fail-sick rock, I think most of them are probably from the ferrosilicate.
Okay, I got you. Okay. So another thing is, can you provide a little bit more details about how to incorporate advection in FreeQC modeling? Because I haven't seen that quite often before.
Yeah, so there's a transport data block, and so it simulates both diffusive and advective transport. So you can use it, and you can specify the whether you want diffusion only, or you can input a advection rate and it'll simulate that.
Okay, great, cool, thank you.
Hi, I'm Lucia Bellino, UT Austin, and my question is also for Rachel. Great talk, and I think really exciting. I was wondering if you anticipate this masking of the signal to be unique just to magnesium-rich sulfate and siderite, or if you think maybe this is the start of understanding or anticipating if there are other minerals that could be masking the signal of carbonates, or if other carbonates like calcite or magnesite might also be masked by sulfates.
Yeah, I think it's definitely an area for further exploration. So on the masking side, in the cohort with magnesium sulfate, I think other polyhydrated sulfates are a really strong contender. I think both the width and depth of the 1.4 and 1.9, and then this really strong absorbing after 2.2, I think that's a big part of what is wiping out these diagnostic carbonate absorptions. And then yeah, I hadn't started to think about other things that could be in the masked cohort, but I think that's important to explore as well for some of these other features that we've wondered if they're on Mars and we haven't been able to spectrally identify them. So yeah, I think it's an exciting area. So if other people want to do experiments exploring some of that, I think it's very promising. Yeah.
Thank you.
Thank you.
Hi, Katya Yanis, Brown University. My question is also for Rachel online. And I wanted to ask about your methods and whether or not you had any variation on your grain size, because that may also affect the shape of your spectra.
Yeah, so we did not sieve the grains. I think that's another interesting thing that could be explored. So we ground both of the phases, but they were sort of a bucket of 250 to 700 microns. It's a bit heterogeneous. I thought that was fine, as that's the grain size of a lot of what we see in Gale, and it gives a little bit of verisimilitude for how some of these phases might interact with each other, the fact that there are going to be slightly different grain sizes together. But we did not sieve them, and I think that could be an interesting additional area to explore as well.
And if I could ask a follow-up, I also was wondering, because you mentioned that potentially carbonates are just not there because they may have been destroyed. Is there any other, perhaps iron oxide or any other iron mineral phases that you expect to see if carbonates were destroyed, and whether or not that could be a clue?
Oh, on trying to distinguish if the carbonates did form and are obscured versus didn't form?
Yeah, correct.
Yeah, I think there is a lot of work on that and arguments for sort of why maybe some of these acidic phases could have destroyed some of the carbonates and why that's maybe consistent with what we see. And I think there are a lot of arguments for about like the atmospheric CO2 content and if that's even consistent with having widespread carbonate formation. But I don't have any particular comment on that from this project.
From potential acidic conditions, that may be some reason.
Yeah.
But thank you.
Yeah, definitely.
All right. I have another question for Dr. Shepard. Fantastic talk. Thank you. I'm really curious, and I know you're working in Gale, but I think looking at Jezero as a case study for this is quite intriguing, because Jezero is a place where we did see carbonates from orbit, and now that we're on the ground there, we see intimate mixes of carbonates and sulfates everywhere. So kind of the question of how we see the carbonates in Jezero with the sulfates and not anywhere else, could that be a helpful case study both in situ and orbitally to try and deconvolve those mixtures?
Super helpful. Yeah, that's really interesting. I've been wondering how this manifests in Jezero, and I think it's also part of this constant pattern of things are always more complicated when we see them on the ground, especially in terms of the carbonate mineralogy and then also the sulfate mineralogy. Like we're always seeing more sulfates and a wider variety of sulfates on the ground than we see from orbit, and why that is very interesting when all of these things have very diagnostic absorptions. And so why are they not manifesting in orbit so consistently? So yeah, I'd be really interested to talk about how it looks at Jezero.
Thank you.
Kaushik Mitra, University of Texas, San Antonio. My question is for William. I promise I remembered the name of your sample when I was sitting there, but by the time I just forgot.
Mapiripana.
Exactly. So it's in the amapari marker band, right? So that thing. So amapari marker band is like rich in iron, manganese, zinc, chlorine, bromine. So highest concentrations of all of these things, right? Based on Lucius Thompson's study that came out. The similar thing that you're doing for iron and iron carbonates, can we do something about understanding what is the manganese phase that is there and what is the zinc phase that is there?
That's an excellent question. So we were hoping Mapiripana to show up obvious data to elucidate that. The issue is that it has manganese enrichment, but it's not standing out compared to the rest of the Amapari marker band. So it's possible some of this manganese is in the rhodochrosite. We cannot rule it out, but we cannot prove it. So there is enough carbonate to make it, but the uncertainty is so high on the carbon signal that all of it could also just be in siderite. We are
Our next step is, of course, to run the model that we mentioned, but also to run the uncertainty on chemical composition. We ought to do that correctly. So
Yeah, understanding like the oxidation state of manganese would be like.
I agree.
Right. Thank you so much.
Thank you.
Hey, Adrian Bros, Purdue. Question for William. I noticed from a couple of the slides that the area right below the marker band unconformity seemed to be like a mishmashed light tone layer, something perhaps akin to like a diagenetic zone. I know gentleman right behind me, Bill, had an abstract on that, considering it's something like a diagenetic zone. I'm wondering if there's anything that zone, based on analysis that may or may not have taken place on that, ChemChem, APXS, et cetera, can that tell us about the environment prior to the deposition of the marker band, the lacustrine, likely lacustrine environment? And is there any siderite in that lower bedrock layer that is massive and disrupted right beneath the unconformity? Thank you.
Yeah, you're right. Since it's direct contact with that underlying strata, indeed, it's key to understand that underlying strata. We have, unfortunately, as you know, the contact is hardly visible because there is a sharp contrast of erosion resistance. So we have some chem data showing that it's sulfate rich, and there is also data that Bill has presented showing that there are sulfates there in an amount that's quite unusual compared to what we've seen elsewhere. The other data we have from that, because the marker, we have a larger scale data that shows this is likely an unconformable surface. So we think there is our current hypothesis that there is a supersurface and erosion, a deflation in that surface, and then Mapiripana, the lake deposit, was done just on top. And so you're right, it's quite a stark change in environment, and it seems to be like a flooding of low energy of some sort. And indeed, in the horizon below, there could be a pedogenesis of sulfates. There are early diagenesis, or diagenesis also late in some cases, but the sequence is really interesting. There is a sharp change of mineralogy there.
Thank you.
Before the next questioner goes, I had a question actually for Anushree Srivastava, the speaker who presented the Sherlock hydrated carbonate results. And my question was, could you elaborate on what environmental conditions Nescaronite records? And can it help us test between the lacustrine and altered igneous hypotheses for the margin unit, or is it not particularly discriminatory? Thank you.
Oh, so to answer the first part of the question, I mean, finding Nescaronite on the surface of Mars is really diagnostic to alkaline environment. That's the first thing that comes to our mind. And yes, I think that's the key question that we are still trying to figure out, that what's making this particular mineral to deposit there and to stay hydrated for such a long period of time. It requires alkalinity, it requires optimal temperature, pressure. Yeah, so that's still a question. And to answer the second part of your question, again, it's really complex to really answer that. I mean, Nescaronite has been found on a bedrock that is classified as sedimentary. So I guess that's all I can define at this point of time. That there's a lot of studies that still needs to be done. And I was just finishing off with the sample return prospect of the mission. We have collected the sample from that bedrock, so we will be able to answer these complex questions when we have the sample back here on Earth in the future, maybe.
Thank you.
One last quick question, because we're running a little behind. Oh, go for it, Bill.
Go ahead. Oh, yeah. Bill Farron, Space Science Institute. I just wanted to point out both to Janice Bishop's question, and I think also with regards to the remote sensing aspect, that any mass cam multispectral data didn't see any kind of a stronger downturn like you might associate with siderite, and also that the Mapiripana, the facies is pretty small, and the narrow Barker band itself isn't that big, and that's a subsection of it. So, you're probably not going to see it with Chrism.
Thank you. Let's thank our speakers one more time. And if our next speaker can walk up. Our next speaker, Merv Yasilbas, will be telling us about detecting frozen biosignatures using Raman spectroscopy.
So hello everyone, I'm Merve Yeşilbaş, and now I'm going to show you some of my exploratory research from how to detect the frozen biosignatures on ice. And now how to go
big green button.
Like this. And now that's in the first slide that you see, we know what's the biosignature? A biosignature is the object pattern or molecule. It's like that resembles the life. And it can be anything. And biosignature detection is super complicated, especially when it's involved with the rocks. And biosignature to detect, sometimes even not one single instrument is enough for this. But besides that, like in the Perseverance rover, we have Raman spectroscopy, which is one of the most strong methods ever to distinguish the inorganic and organic materials. And here in this study that I will show you some of the results that I have been done using the green laser 532 nanometer, which is actually similar with the SuperChem instruments and in situ measurements. And here is the Jezero crater. We have been talking a lot about this and the mineralogy. We have in the Jezero crater, that's in the western, that's the inner margin, that's the marginal carbonates. It's the typical of the hydrated magnesium carbonates and also the carbonates, magnesium carbonates. And of course, that's the ultramafic and the mafic minerals. And also in the delta area, we have the clay minerals, the iron, magnesium, smectites. And on the other hand, if we look at the Lake Salda, that's located in the southwestern of Turkey, and it's actually the geologically quite young area. And here we also have very much similar mineralogy, that's the Jezero crater. We have the alluvial fan delta here, it also has a lot of different type of the ultramafic and the mafic rocks, and along the shoreline, we have a lot of the hydrated magnesium carbonate deposits are deposited there. So which is actually the excellent area to study, the Jezero crater. And we know we are the geochemists. And if you have this type of the rocks, especially if you have the clay minerals and magnesium carbonates, they are the little time capsules to store the water, the atmospheric gases, and also the biosignatures. So a wise geochemist knows and feel happy whenever you detect them anywhere in the solar system. And then in the next slide, Lake Salda has one difference from Jezero crater because we have a living lake. This is the evaporative magnesium-rich alkaline lake, which is also quite similar to Mars. And here in this lake water, we also have a lot of type of the hydromagnesite-rich samples. And then to these samples here, which is also quite unique, is the lake samples here, we have actually interacted and deposited and precipitated through the help of the microbes, and they form hydromagnesites, forming microbialites there. And in here, in this study, I use the 3 different samples that's collected from the fun area, and also plus the microbialite island. Here, that's the gravels, sediments, and lake water. Gravels and sediments, I turn into them to the powder form before the experiments and to interact with them with the lake water. And here is the first analysis to characterize these samples. To characterize the samples, we use the very much different techniques: Raman spectroscopy, infrared spectroscopy, scanning and optical microscope. Plus, we have also used another X-ray diffraction techniques to make sure what type of the sample mineral faces that we have. And as we expected in this sample, they are natural samples, and we have the gravel sediments and even lake water. They are quite rich with hydromagnesite, and also we have very much especially in the sediments, that we have the different form of serpentines and also a little bit minor traces of the titanium dioxide. And we have in the gravels different form of the calcium carbonate aragonites. And in the organic wise, they have a lot of type of the beta carotinate signatures. And especially with the sediments, that's the part that's interacted with the lake water, it has much more organic signature if we compare with the gravels. And here is the spectrum of the Raman spectroscopy. And the Raman spectroscopy with the green laser is actually that's the very much good to give the hydromagnesite spectra. It's very much different when that's the previous talk, as you see, because we have the Raman active group in the structural OH in the 3649, and we have the crystalline waters like 2 doublet signatures in the water stretching region. Plus we have the very much that's the carbonate signature in the 1119 per centimeter. So it's very lucky that we can collect this very nice spectra, and we have also several bands below to 400 centimeter just to confirm it's a very nice, close to pure hydromagnesites. And here is the temperature effect, and it's the hydromagnesite gravels powder that has been exposed to the temperature. And what we have seen in these results, that the temperature has actually nearly no impact on this. So we have only seen that's a very much slightly shift, that's from 1 to 3 per centimeter shift. And then during the temperature change, we haven't seen any other except the structural water crystalline bands is like become much more distinct, depends on the OH coordination region. We haven't seen anything that's observable here. And here that's what I have done here to use multivariate curved solution alternating least square analysis system. That's a chemometrical method actually to find out what type of the samples that you have and the mixture inside, plus how can it's distributed between the sample. So and also that's what you can do with this model is that you can extract from the pure spectral components with the concentration profile. This is the concentration profile that refers to any other experimental parameters that you refer. This can be temperature, pressure, pH, or any other variable factor that you use. And here, this was the first results to test the model with the much more complex organic sample with the hydromagnesite. What we have seen here is that's the perfectly located, that's the water stretching region, ice and hydromagnesite, they aggregated together. And in the next slide, when we see that's the carbonate region, it's much more complicated. Well, actually, it's a successful model because we have seen that the red dots, which it's just like correlated with the same model, component 1 and component 3 is actually shows that's the mixture of the hydromagnesite and keratonate, and they are very similar each other and following each other. So that shows that's actually good. But there is one little guy and little band here that's very much like that needs to be distinguished more. Because what is the nature of it? Here's the question. It's complicated, especially in the low wave number region. And it's also like that, so we need to check wet dry cycle, temperature effect. Is it coming from the hydromagnesite mineral itself, or is just like the nature of carotenoids? Then there's the next experiment, because I don't have any actual purified keratinoid. I use the synthetic keratinoid and freeze them. And between these experiments, that's what has been realized. Actually in the dry wet cycles in the spectrum, we have the peak band intensity ratio is quite same. Well, beta carotenoid is a very low soluble material. And then when we go to the temperature is actually the mostly effect. That affects the band of the spectrum here. So temperature matters. And then to the next experiment, the very last one, we have been worked with basically that's the much more simple hydromagnesite mixed with the rock gravels, with the beta carotene, and also the lake water. And then in this experiment, what we have seen that was quite interesting, beta carotene is actually widely distributed and freely located, even in the icy conditions. And then we have as we see in component 2 and 4, we have seen that they have been just still prove that they are still, even in the presence of the hydromagnesite, they are just located freely. But look at the component 2 here in the top. When the ice is formed, ice help to lock to beta carotenate within the help of the mineral, within the hydromagnesite. And here in these experiments, that is actually to show us, if you want to detect that's the only minerals and also the icy mixtures, water stretching region is the perfect, and it's the much more complex region. But if you focus on the low wave number region, then you will have a lot of a complicated issue. But now we know that the beta carotenate is the one that has a lot of change, dry wet spectral change responses, and also affected by a little bit minorly affected by temperature. But then most importantly that we see, which was also interesting, beta carotenes are absorbed on just like hydromagnesite minerals and stabilize there at -40. I have tried at -10. It was not like that. So just a peek. Side note. And in the next slide, I just want to show you that's my PhD student room will give more IC spectroscopy data. And also if you want to know more about the neutronites and also the sulfate salts, you are very welcome on Thursday. Thank you so much.
Thank you. Our next speaker is Ralston Silas, and will be presenting on the mineralogical characterization of a potential Mars analog field site.
Okay, thank you all for sticking around late into this afternoon session. My name is S.J. Ralston. I use they, them pronouns on behalf of myself and my co-authors, particularly my co-investigator, Dr. Diti Pandey. I'd like to tell you about a field site out in New Mexico that we investigated specifically for its formations of gypsum and carbonate as they relate to Mars. So why are we interested in sulfate and carbonate in particular? We've heard a lot about that through this session so far, but I just want to emphasize that sulfate is really common on the Martian surface, shown in that top image in pink. We see it all over the place, and we see lots of different expressions of it sedimentologically, which means that it probably formed in a variety of different conditions. We do see lots of different kinds of sulfate, but one of the more common ones is calcium sulfate. We see gypsum dunes at the North Poles, and we see calcium sulfate veins in Gale Crater. So that seems to be a fairly common type of sulfate on the Mars surface. Carbonate, on the other hand, as shown in the lower picture in green, is a lot less common, at least in terms of what we can detect on the Mars surface. It seems to be limited in extent with few outcrops over the surface. That's even though our models of the early Mars climate predict that we should be forming a lot of carbonate on early Mars with a thick CO2 atmosphere and near neutral to alkaline waters. And the carbonates that we see on Mars are primarily iron and magnesium carbonates, although some calcium carbonates do exist, calcium iron carbonates in Mars meteorites. But the interesting thing about these sulfates and carbonates, at least to me, is that we don't really see calcium sulfate and calcium carbonate in the same place at the same time. They seem to be mutually exclusive, at least as far as we can detect. And this is interesting because, as we've seen in some of the talks earlier today, calcium carbonate is pretty easy to form. It's one of the first things to precipitate out of a solution where you have carbonates and calcium both together. So why is that? One of the ways we might be able to answer this is with analogs. So we could find a terrestrial analog that has both carbonate and sulfate and try and relate it back to Mars to understand how the carbonates and sulfates on Mars formed. So ideally, this terrestrial analog would have lots of calcium sulfate and not a lot of calcium carbonate, and would also have both minerals, but the two minerals are not occurring together. So that would be sort of our ideal analog. The place that we investigated to try and meet these conditions was the Quebradas backcountry in New Mexico. It's about 6 miles east of Socorro, about 2 hours south of Albuquerque driving on Piro tribal land. It records Pennsylvanian and Permian sediments, so the climate transition from cold and wet climate to a warmer, more arid climate. And it has carbonates, sulfates, and some clay minerals as well, which is nice because we also see those on Mars. And while a lot of the paleontology in this area is pretty well studied, there's a lot of cool paleontology out there, the mineralogy and geochemistry are not as well studied. So we wanted to go out there and study these minerals, understand how they were deposited, and figure out if this site was a good Mars analog. So we looked at 2 sites in particular. The first was the late Pennsylvanian Tinajas member, which I'll just call Tinajas from now on. It formed in the Pennsylvanian, like I said, so a cold and wet climate in what is probably a Sabkha-like environment, so coastal environment, cyclically flooded and evaporative by turns, and is described as being gypsum-rich carbonate beds in the literature. You see what I mean about the mineralogy being understudied. The second site was the Los Valos Formation, which is a Permian site, so it's a little bit later, a little bit warmer, a little bit drier when it was deposited. And this is mostly gypsum, so massive gypsum deposits with some beds of clay minerals and dolomite. And this is also supposedly in a Sabkha environment, so cyclically flooded, evaporative, but under a much warmer, more arid climate. All right, so when we went to these sites, what we wanted to know was, what is the mineralogy? How were the minerals deposited? What conditions allowed sulfates and carbonates to be present together, if indeed they were present together? And is this a good analog for processes that were ongoing on ancient Mars? So we collected samples from these two sites. Mostly we just went with hand samples, sometimes with our actual hands. Brought them back to Johnson Space Center for analysis. And we mainly did quantitative X-ray diffraction. We used an internal standard of 20 weight percent corundum so we could get quantitative mineralogy using Rietveld refinement with the Jade Pro software. All right, we did all this. What did we find? We'll start with the Tinajas outcrop. It's a very small outcrop. It's only about 2 feet tall. And it breaks down into 3 main zones, not necessarily 3 layers, but 3 main zones. The lower one is very gypsum rich. It's about 70% gypsum by weight, with a good deal of amorphous material and a little bit of basanite, and then some trace minerals that were below the 1 weight percent detection limit of our XRD instrument. So that's the bottom layer. Above that, we have these sort of intercalated blocky layers of carbonate in the middle there. And they are almost entirely calcite with a little bit of amorphous material and quartz. So very calcite rich. Interestingly, no sulfate in there. And then on top of that was the biggest surprise of this trip, which was a sulfate layer that was not gypsum at all, but was celestine, which is a strontium sulfate, which has not been previously reported in Quebradas. And we also see a large amount of calcite in this material, about 17 weight percent calcite. So that was very interesting that we have carbonates and sulfates mixed together, but not calcium carbonate and calcium sulfate. So interesting result right there. Over at the Los Valos outcrop, first of all, it's a much larger outcrop. It's about 6 feet tall. But it also breaks down into 3 main zones. Again, the lower zone is very gypsum rich. It's about 79 weight percent gypsum, some amorphous material, a little bit of basanite. A tiny bit of calcite, about 2 weight percent, which we suspect is contamination from all of the limestone dust that's blowing around in this area from all of the limestone. Above that, we see this sort of gnarly layer with calcite, amorphous material, quartz, and a lot of clay minerals. We haven't completely nailed down what the clay minerals are, but it's most likely mica, illite, something like that. So we suspect that it's detrital rather than authigenic because we don't see any other evidence of high temperature stuff ongoing here. So probably detrital clays with a bunch of calcite. And on top of that, these blockier, better consolidated layers are mostly calcite and dolomite with a good deal of amorphous material. And again, a little bit of gypsum, which we think is probably contamination from all of the other gypsum that's blowing around in this area. All right, that's what we found. What does it mean? So we have these 2 deposits that formed in nominally similar environments, but came out very differently. And this is possibly due to the climate differences between them, that Tinajas was laid down in a much cooler, wetter environment. Maybe it was less well preserved because of that. But it's also possible that the Tinajas underwent a good bit of alteration after it was laid down. We see this intermingling of carbonate and sulfate. Again, calcium carbonate with strontium sulfate, not the 2 calciums together. And we see this abundant celestine, which is a weird mineral to find. Whereas over at Los Valos, we have calcium carbonate and calcium sulfate, but they are separated by this layer of, this clay-rich layer. So potentially a passivating layer or an impermeable layer that prevented the 2 from being in communication with each other. We also see more basanite and less amorphous material consistent with that deposit being laid down in a warmer, more arid environment. And a capping unit may have resulted in it being better preserved. There's not just those big, thick carbonates. There's also a sandstone on top of that that may have prevented it from being just completely worn down like the Tinajas. So if you're like me, you saw that celestine and went, how did that get there? And we think that this is a product of diagenesis. There's a great paper by Hanar et al. In 2004 looking at large celestine deposits in places like Greenland, Germany, Italy. And they find that it's probably a diagenetic product, that you have an evaporative environment where you lay down a bunch of calcium sulfate and you get water that is having strontium concentrated in it due to evaporation and possibly due to leaching strontium out of marine carbonates that it is passing through as they supply some porosity and permeability as this water begins to infiltrate. And then you have this strontium-rich water coming into contact with calcium-rich sediments, and a replacement reaction happens because strontium sulfate is much less soluble than calcium sulfate. So let's go back to our big question. Is this a good Mars analog? Well, we did not find a place that was sulfate-rich and carbonate-poor. It's got a lot of sulfate and a lot of carbonate. No analog is perfect. Some analogs are useful. However, we did find that calcium sulfates and calcium carbonates do not occur together, and we think that this is a good place to understand why that is happening on Mars. I will skip through to the end, throw up my acknowledgements, and also say on behalf of myself and my other trans colleagues, please stop holding this conference in Texas so we can continue to attend. Thank you.
Thank you. Our next speaker is Rachel Slank, and will be telling us today about early Mars habitability as constrained by sediment magma interactions in a hydrothermal dike system in Utah.
Thank you for that introduction. So as he said, my name is Rachel Slank, and today I'm going to talk a little bit about the work I did at my postdoc at the Lunar and Planetary Institute. So jumping right in, the Martian crust is predominantly composed of basalt, and it has a lot of other alteration materials on the surface. Now, these can be caused by a wide range variety of processes, going from volcanic to sedimentary to kind of everything in between. And while we're seeing a lot of these alteration things, we should also be seeing high temperature hydrothermal systems. However, that can be from volcanic or impact, but we're not really seeing a lot of evidence of this from orbit. And because of that, we have to look for different ways to find evidence of this. So what we wanted to do was look at Earth analogs, see if we can understand it on Earth, and then take what we learn and then bring it back to Mars to help constrain scenarios or locations where we might find this high temperature hydrothermal system. So our goal was to investigate a mafic dike and its surrounding hydrothermal system to kind of analyze this magma sediment interaction, looking at its mineralogy, its mineral formation, its alteration, the whole evolution of the system, and if it could be habitable. And then taking everything we learned here on Earth and then seeing if there's a spot that is analogous on Mars. So this is our field site. It is in the Colorado Plateau in south central Utah. It was a mafic dike that intruded in the Entrada sandstone. So our dike, DC dike, is part of the San Rafael volcanic field. So it's about 3.8 to 4.6 million years old. And as I said, it had intruded into this Entrada sandstone, which is Jurassic in age. So about 140 to 180 years. So if you'll see in the upper image on the far left, that tannish red color is that Entrada sandstone. It's iron silty. And then you have the dike, which is more of that gray black. But what I really want to draw your attention to is that far right image. I have a laser pointer, haha, where we have these xenolith crystal pockets that were found throughout the entire dike system. And I want to bring this up because as you sample the dike, these have to be included. And so we wanted to get a wide range of both the dike and the contact rock. So we took 3 samples of the altered contact rock, 3 of the dike in different locations. So the way DC dike is intruded, you almost have it as an arch, where you have a left-hand side, a lot of contact rock in the middle, and then a right-hand side of the dike. So the left-hand side of the dike is composed of 2 different contact rocks, 67 and 69, with our dike in the middle at 68. You can see the hand samples over here on the left-hand side. And the right-hand side of the dike, our contact rock is 70. 71 is predominantly the dike, and 72 is predominantly those xenolith crystal pockets. Now I say predominantly because as you see over here in our rock samples, 71, whoop, wrong way, sorry, I want the laser pointer, haha. 71 has a little bit of those crystal pockets, but it is predominantly the dike. However, it is over at 72 where you see almost completely those crystal pockets, but a little bit of the dike is attached. So why am I explaining this? As we're starting to look at the mineralogy, which is a main point of our methods, we're going to see both in both of these samples. So our methods, we used 3 different techniques. We used VNIR, XRD, and thin sections. And the reason we use these 3 techniques is as we're looking for analogous spots on Mars, we also want to use instruments that have analogous instruments on Mars. So with our VNIR, you have CRISM and SuperCam that is analogous on Mars or in orbit of Mars. For XRD, we actually did quite a few techniques, including bulk multiple soil sample sizes and that spiked corundum that SJ talked about, where we're able to actually get weight percents of our minerals. And on Mars, you have ChemMin. And then for our thin sections, where we're able to kind of get a very close-up look of the minerals and its alteration and formation, you have Pixel, where we're also able to see that on Mars. So due to time, we're not going to be able to talk about the VNIR, but we can talk a little bit about some of the XRD. I want to focus on that spiked XRD results, since that is giving you the actual mineral percents. But we did take quite a few other different techniques. And so when I show you these pie charts, the bright fun colors are going to be that spike data. And so with the legend, you have the mineral with it. But if the mineral was detected in a different XRD run, but not in the spiked, I still wanted to show what those were. So they're going to be listed in the legend with an asterisk. And then if they're in bold, they were also detected with the VNIR. So starting with our contact rocks, I'm actually going to focus on that inner arch first, so 69 and 70. You're going to see they look really similar. 2% of each other with quartz, 2% with plagioclase, and then they have the same amount of montmorillonite and other amorphous materials. Then looking at that other contact rock, 67, which is that far left one, you still have that plage, that quartz and montmorillonite, but you also add calcite into the mix. Now with all three of these sites, we also have other minerals detected, including jarosite, vermiculite, and biotite, just to name a few. Going over to the dikes themselves and their samples with 68, which is that far left dike, you have quartz, plagioclase, calcite, montmorillonite, or other amorphous materials, CPX, or those, and then biotite. Going over to 71, you lose your calcite, but we still have plagioclase, montmorillonite, those CPXs and biotite, but you add in sanidine and vermiculite. Now, both the vermiculite and the sanidine were detected in 68 in different XRD runs, just like the calcite was detected in 71. Also in 71, lizardite and cristobalite were detected. Then looking over at 72, which has those xenolith pockets, it is predominantly calcite, which makes sense, right? You have those crystals, but you still have a large amount of the dike as well, which you see in the other two samples. So now looking really quick at the thin sections, for our dikes, the dike started out as an olivine basalt, which you see right over here in A, but that olivine was replaced with calcite. The pyroxene broke down to biotite and in some cases vermiculite, which you see really nicely in C and D. And then the plagioclase and other mesostasis minerals broke down to montmorillonite. Our contact rocks are a little bit messier because you had a fluid moving around the system. So the entrada started out as quartz, plagioclase, and a calcite cement with iron. The quartz stayed, but it really wasn't happy, right? It didn't react, but it had that undulating extinction. You had your plagioclase break down to montmorillonite, and the calcite broke down and actually left the system and came back, at least once, but most likely a few times, based on the different textures that you're seeing in that calcite. Cool. We have our minerals, we have the mineral formation, we kind of see some of those alterations. What does that really mean? What was the whole story? DC dike intruded into the Entrada sandstone. That heat caused the groundwater around it to heat up and create a hydrothermal system. That hydrothermal fluid then brought other elements into the mix. And that fluid, as it cooled, precipitated other minerals like jarosite, fluorite, vermiculite, and other carbonates like siderite. The fluid, the calcite, and the sanidine precipitated out to montmorillonite. And then the iron, which both came in the fluid and the original entrada, ended up causing some iron staining. But we're not entirely sure of that timing. So in conclusion, for our site on Earth, we had minerals that prove it was a mafic hydrothermal system. We had a lot of alteration minerals. We saw that there was fluid moving throughout the system. We also saw a lot of range in the minerals over time. We had a large range of temperatures. We had cristobalite all the way down to jarosite and montmorillonite, so really hot to pretty decently cool. Our pH was fairly neutral to a little bit of alkaline, except for jarosite. Unfortunately, I couldn't talk about it in the 10 minutes, but we did look at its habitability potential. And after about 120 degrees Celsius, this site and this system was habitable, but it would have started out as extremophiles, like the thermophiles and then some of the more pH extremophiles. But is this a great spot for Mars? Well, starting with Jezero, right, we actually found that quite a few of our minerals in the system matched minerals found at Jezero. We had olivine, we had plage, cristobalite, vermiculite, siderite, and jarosite, just to name a few. Now, I want to pause really quick and say that just because I am not saying one system caused all of these minerals on Jezero, I am saying that our site proves that one system could cause all of these minerals. But with that, we're continuing to explore additional locations on Mars, and I am out of time, so I thank you, and I'll take questions in a bit.
Up next, we have Megan Barrington talking about the spectral effects of progressive weathering and applications to Jezero Crater Mars.
Thank you for the introduction. And with the slides, I'll go ahead and get started. Okay, perfect. So we're going back to Jezero's crater floor. So as a brief refresher for everyone here, Jezero's crater floor is composed of two major formations, Seta and Maz, where Seta is interpreted as an olivine cumulate. Maybe it had a more felsic component that was kind of on top of that, but has since eroded away in the past. Whereas Maz is interpreted to be a series of basaltic to basaltic andesitic lava flows, and the composition of those lava flows varies between members of the Maz formation. So this is just to show you what the Maz formation actually looks like. Maz is stratigraphically on top of the Seta formation and can be broken down into these three groupings that were described by Udry et al. In 2022. So we have lower Maz, which is made of Artubi and Rochette. Rubion is a transitional member, and Natani and Shesh at the top make upper Maz. So stratigraphically beneath that, you have the Seta formation, which is composed of the members Isol, Bastide, and Contant. And important to note here is that although we observed Contant in the Seta formation, it's actually compositionally a lot more similar to the Maz formation. So we interpret that it's very likely a separate lava flow that's petrogenically linked to Maz. So the composition of these units varies significantly. So Seta is broadly composed of FO55 olivine, augite, and feldspars, whereas Maz is just the iron-rich feldspars, or iron-rich augites and feldspars. And upper Maz is very enriched in silica content at about 52% on average. Lower Maz and Rubion are slightly less enriched at about 46 to 49% on average of silica. And Contant is more similar to upper Maz in its silica content at about 53% on average. So in addition to that compositional variability that we observed, there is a complex emplacement and exhumation and alteration history that we're working with that can have complex spectral effects on MassCAM-Z spectra. So we want to address three primary questions here today. The first is to define the rates of co-evolving spectral changes that are associated with one aspect of weathering, which is oxidation. So if there's any variability between the rates of those co-evolving features, we want to describe why that variability is occurring. Secondly, we want to address the relative exposure ages of geologic members of Jezero's crater floor. And in particular, we want to see if Contant has any evidence of being linked to Seta or Maz definitively. And thirdly, we want to ask the question of the relative importance of pre-exhumation and post-exhumation oxidation in these crater floor members. So in order to address these questions, we collected multispectral ROIs using MassCAM-Z, which you probably know by now is a stereoscopic, zoomable, and multispectral imaging system on the Perseverance rover. And we collected ROIs from natural surfaces, abrasion patches, abrasion tailings, and drill tailings for this analysis. That data is complemented by terrestrial analog data from 3 different field sites with a range of compositions that encompass what we observe in Jezero's crater floor. So they really range from intermediate to mafic. And we also used the Mass-Camz analog spectral imager, which is our analog to Mass-Camz built at Cornell University, to collect our terrestrial field data. And it was complemented by visible and near-infrared spectra from the ASD Panalytical Field Spec TREC, which covers a range of 350 to about 2,500 nanometers. So the spectral features that we were using for our analysis were the 528 nanometer band depth, which is associated broadly with ferric oxides, BD866, or the 866 nanometer band depth, which is associated with crystalline hematite, the ratio of 754 over 442, which we call spectral redness, where higher values are associated with increased oxidation, the ratio of 677 nanometers over 605 nanometers, where values greater than 1 are associated with ferric phases, and values less than 1 are associated with ferrous phases. And finally, the near-infrared ratio of 800 nanometers over 1022 nanometers. So here, values greater than 1 are broadly consistent with olivine, as you can see in this figure, and values less than 1 can be interpreted sometimes as iron meteorites, although we haven't observed those in Jezero Crater. But with a combination of this value and other values, you may also be looking at a hematite spectrum, as we are in this figure. So this is a brief overview of the field sites that we visited for our terrestrial analog work. We visited Colshan Ridge andesites, the Columbia River basalts, which actually is composed of 2 separate field sites, Potholes Coulee and Frenchman Springs Coulee, and the Twin Sisters Mountains, which are composed of dunites. And all of these are located in Washington State. So compositionally, the suite that we're looking at is things are more intermediate on the left, mafic in the center, and ultra mafic on the right. So you're becoming more mafic from left to right. You'll have to pardon the typo there. And you're also decreasing in silica content with that transition. So to assess how these co-evolving spectral features are evolving linearly, we plotted the BD528 value versus spectral redness and then performed a linear fit at 95% confidence. And we found that for Maz, Contant, and Seta, all analyzed separately, that these slopes of these ratios were identical, which was interesting. However, when we compare it to our terrestrial data, we found that the terrestrial field sites all had unique slopes. And so we interpreted this to mean that although there is compositional differences in both of these sites, we're really seeing varying weathering conditions and varying weathering products that are happening for our terrestrial data set, which likewise means that we're seeing more similar oxidizing and weathering conditions in Maz and Seta and Contant. So using this same ratio, we split the range of values for Maz, Contant, and Seta into 4 equally sized groups and assigned them a value from 0 to 3, where 0 is least weathered, 1 is lightly weathered, 2 is moderately weathered, and 3 is highly weathered. We then used these assignments to track their progression through a known parameter space that was used by Rice et al. To highlight the spectral differences between Maz and Seta. So we're really able to compare how those spectral features are related to changing the spectral features in other ways. So we found that we were able to produce 2 distinct groupings for Maz and Contant, and that the values associated with this oxidation progression have the effect from going to the least weathered to lightly weathered ROIs of increasing both your 677 over 605 ratio and the near infrared ratio. However, there's no additional change after that initial stage of weathering that makes any kind of predictable change in this parameter space. But for Seta, we do see predictable changes in this parameter space with increased oxidation. So going from the most lightly weathered to slightly more weathered and then up to moderately weathered, we can produce 3 distinct groupings. So the spectral changes are more predictable for the dunites than they are for the more intermediate to mafic compositions. So to address the exhumation histories of Jezero Crater, we plotted the BD528 value versus stratigraphy. So stratigraphy is broadly increasing from left to right. Here we see that the maxima increase with stratigraphy within each formation, and that this could be consistent with top-down oxidation of these surfaces. And this is also consistent with the fact that Seta was never completely covered by the Moz formation. You see that Seta has slightly higher values than some of the lower values of Moz. And so here you can see that Moz has kind of embayed the exposure of Seta that we observed and rather than covered it. And finally, the band depth for 866 associated with hematite broadly follows the same trend, although Contant may be an outlier here, perhaps signaling that it experienced some aqueous alteration before further emplacement occurred on top of it. And these low hematite values are consistent with limited water to rock interactions that we've observed in Jezero Crater in the past. So in conclusion, the rates of those co-evolving spectral signatures do vary as a result of the weathering products produced. And in Seta, moderate to high amounts of oxidation do produce changes in both 677/605 and 800/1022 ratios, but those are not very distinguishable after initial stages of oxidation for Moz and Contant. And ferric oxide and hematite signatures also trend such that they appear to be dominated by post-exhumation oxidation and are also consistent with top-down oxidation processes. But Contant may be an outlier here, perhaps experiencing some aqueous alteration before its further burial. And finally, low hematite band depths are consistent with past interpretations of limited water and rock interactions in Jezero's crater floor. Thank you so much.
Right on time. We'll ask our speakers to come back up to the stage so they can answer questions in the final Q&A section. And again, we'll take questions in the room and online.
Both of you. I love both of you. Hell yeah. Very nice. Yeah.
Hi, you guys. Shelby Osborne, University of Arkansas Center for Space and Planetary Sciences. My question's for Rachel. I was just wondering if you found any water-soluble carbonaceous salts, such as like sodium carbonate, and if the presence of these salts would also affect the other water-soluble minerals also found in the dike system.
So I'm a salty person, and I was very sad that we didn't have any salt that I was able to detect. I know some of the other dikes in our area did, but my dike did not have any.
And do you think that is truly reflective of the Jezero crater site or no?
No, I mean, just because our analog dike didn't have it didn't mean that we're not going to find it elsewhere, right? Other dikes had it. Jezero has salts. Mine just didn't. It was a sad day.
That's a little sad. That's okay. You'll find them later. Thank you.
Hey y'all, David Burt, NASA Goddard. Another question for Rachel. Really exciting to see that you've got these similar mineralogies. Can you speak to, are these going to be able to help us identify these hydrothermal systems better from orbit or from in situ detections?
I hope so. The answer is yes and no. Obviously, this was a 10-minute talk. I actually had 4 sites that I had pulled, a few from orbit and a few from in situ. And when you looked at orbit, you had some, but not all of them. You really need that ground data to be able to be like, yes, this is absolutely hydrothermal. Yes, we have a zoomed in. This is obviously an alteration mineral. Look how cool it looks. From orbit, you can only get so much at just not the best scales.
Totally.
But we're hoping.
Sorry.
Oh, sorry. No, I was just saying, we hope that we'll at least be able to help zoom it in a little.
Gotcha. Looking forward to seeing more.
Thanks.
I have a question for SJ. I was wondering if any of the mineralogy that you saw correlated with, different sedimentology in the bedrock. I also know that, Psabkas are these sort of nearshore environments, but you also get, a sort of transition between evaporative and maybe even like lacustrine or deeper water stuff in this kind of Psabka environment. So did you see that in the sedimentology at all?
So I am not a sedimentologist. One of the things that we did see at the Los Valos site, the really big outcrop, is that if you kind of go around the corner from the place where we took our samples, you see like all of these different layers that have different expressions, and they're all gypsum. So we know that there were different sedimentary environments going on there. There were different depositional environments happening. I don't know enough about sedimentology to speak on whether the depositional environment was affecting the mineralogy, but it is definitely something that is worth looking into, and it's something that some of our colleagues on the gift field team were investigating, was the sedimentology of these areas. Bethany Teeling was looking into that and has produced some really nice strat columns, which we can look forward to in the future.
Would also
so
be-
unfortunately, I don't know.
Would also be interesting to see, because a lot of these sulfates and whatnot and carbonates are in veins in Jezero and Gale. And so, when you're collecting these bedrock samples, are you pulling out these veins from the bedrock that you're looking at, or are you grinding it all up and measuring that?
So we did see some veining in specifically the calcite, probably because it was the only thing that was coherent enough to get veins in it. We were not able to do things on the scale of veins because they were hairline fractures essentially. We may in the future go back and do like thin sections to try and tease out what exactly those are. We also saw in some of those really loose gypsum deposits, there was some like recrystallization into like phenocrysts that were just kind of in there. Yeah, I think it's a really promising site to do that kind of work. It's just, this was a very preliminary excursion just to see like, is it worth going back? And I think the answer to that is yes.
Great, thank you.
Hello, Audrey Putnam, Rice University. I have a question for Rachel about the system you were looking at there. So the intrusion of that dike is much younger than when the sandstone formed. I'm wondering if, and you have these hydrothermal systems that are being set up there, I'm wondering how much that those particular systems that you're looking at were set up after intrusion of the dike, or how much direct interaction of the intruding lava with pore water you observed. And if you think that would be different if you had, the Entrada sandstone that had a lot of pore water versus not very much pore water, on the textures, on the mixing, on the interaction of the lava with the host sediment.
Sorry, I'm thinking. I'm trying to process the entire question.
Sorry.
Can you repeat the first part?
Yeah, so I'm curious about lava sediment interaction when the sediment is still wet and unconsolidated. And obviously
Gotcha.
this is a lot later and it's a very different system, but I'm wondering if the Entrada was above or below water table, would you expect a different interaction of the intrusion of the dike with the surrounding material? And if you would get a more glassy lava, and if that might result in different hydrothermal reactions and systems being set up. I'm just wondering how much, I guess, if you think that there's any control with that on the resulting system.
Yes. So obviously, if it's below water, you're going to have a lot more water. You're going to have more of that glassy. It's going to look different, right? Yeah. The temperature is also going to go a different direction. I don't think ours was, it was more of like that groundwater, not like underwater. But if it was more like you have the hydrothermal vents at the bottom of an ocean, you're going to still get different minerals. We just didn't see that here.
Okay, so you think this is still a good analog for like a dry sediment on Mars or something?
Yes.
Okay, thank you.
Yes.
Adrian Brown, Plant Science Research. So question for, speaking this at the last speaker, you're talking about interactions between SATAR and Mars. In your conclusions, you were saying something like you could conclude that SATAR hadn't interacted fully with Mars or something like that.
I think I meant to imply that SATA and Mars had not interacted much with the water in Jezero Lake.
Okay.
Yeah.
And that's based on the spectrally.
So it's based on several measurements. So previous measurements have shown, I think, that that even though the rocks are a little bit salty, there's not a lot of alteration products that we expected to see in the rocks from water-rock interaction. And the low hematite signatures are pretty consistent with that.
Okay.
If it formed from the water, which is an unknown at some points.
Yeah. Yes. Okay. Thank you.
Thank you.
Hello, I'm Felindia, University of Florida. My question is for Dr. Demaray. Is it Green Blazer? I'm so sorry. I tried.
Stay famous. Yeah.
You spent a few slides talking about beta carotene, and I was unfamiliar with like its importance on Mars. I was wondering if you could say more about that.
Yes, actually, that's the beta carotene is like that's the in nature that's formed by that's the biological that's the product. So it's very much important that's to detect them anywhere on the solar system, and that's the one thing in this study that's the I also wanted to use beta carotene because the first the lake samples and also the sediments they were like that's the beta carotene rich, and I have been using that's the Raman laser and the green laser, which is also quite sensitive to detect beta carotenes in that area. And I thought that would be like a very much good step to make like that's the exploration, how to beta carotenes, if it can be absorbed on the icy conditions. Because Mars is like that's the surface, there's a lot of ice, and also in the near surface is ice presence there. So for me, it's not like, that's my own belief. I believe that if there's any kind of the biosignature, that should be hidden in the near surfaces. So that's also the reason actually why I'm always like, I always say this, I'm sorry, I will say, I'm also looking forward to see the ExoMars rover mission just for this, so we can drill this just in the up to 2 meter in the near surfaces soil. And of course with the Mars sample return, we can detect all the samples in our labs to detect any the little signatures there.
Great,
Thank
you
you.
so much.
Hi, Jordan Chastain, Caltech. I had a quick question for SJ. So you talked about the fact that you don't really see co-occurrence of calcium carbonate and calcium sulfate. I apologize if you said it, but are there lab experiments to show that those just do not occur together? Like the temperature or pressure conditions will make one or the other, or do you think it's more of a environmental aspect that they could occur together, but they just don't?
So the lab experiments that I'm familiar with looking at this are looking specifically at replacement of calcium carbonate by calcium sulfate and vice versa. Because there are places on Earth, I think there are gypsum caves in Italy where you see calcite replacing sulfate, or it might be the other way around. So there is research going into one of them replacing the other. And in those cases, they do occur right next to each other. It may very well be that you have to have really, really specific thermodynamic conditions for them to occur together. But of course, that is like an equilibrium thing. And there are definitely kinetics involved, especially on the carbonate side. So what we were kind of looking for at Quebradas was like, we know there's a bunch of carbonate, we know there's a bunch of gypsum. Can we find a place where they are like coexisting and seem to have been coexisting for a long time? Or is this like a thing that's purely a snapshot and that tells us something about like, maybe Mars has reached more of an equilibrium, maybe there were replacement reactions going on, or maybe it's just like the thermodynamics are on a knife edge and they, tip one way or another. And so that's kind of why we were exploring Quebradas, is to find out like, what kinds of things should we be testing in lab experiments to figure out where co-occurrences would happen and why they don't occur in a lot of places.
Cool. Okay. Thank you.
Yeah, no problem.
I actually had a question for Megan Barrington. And my question was, you showed in your work that throughout the stratigraphy of both Mars and Saturn, that there was kind of maybe a coherent stratigraphic pattern in the degree of oxidation. My question was, how well does our sample suite from those units reflect that degree of oxidation? Like, did we actually sample any of those highly oxidized intervals?
Yes, absolutely. So there are only 2 members of the Saturn Mars formation that I showed that were not sampled. So Natani was not sampled, and there was one more that I think Contant was also not sampled, but the rest of them were abraded and sampled. Yes, so we will be able to get back those samples, do dating on those, and then if the dating confirms these hypotheses, that would be a really cool
cool result, you know, because at this stage, we can say that these results are consistent with oxidation that follows stratigraphy, but we can't definitively say much more until we get those samples back and date them.
Thank you.
Thank you.
Hello, Audrey Putnam, Rice University. I had a question for SJ. It was really interesting that you had so much amorphous material in those rocks, and I'm wondering if you have any geochemical constraints on what that amorphous material is, and any thoughts on how it got preserved as amorphous for this long?
Yeah, it's a great question. And the answer is we don't know. It's one of the things that we are is included in our future work is we are wanting to do bulk geochemistry on these to figure out what all is in there, and then we can subtract out the crystalline component and get sort of rough estimates on what the amorphous material is. And then we also hopefully have some synchrotron time coming up where we are going to look at some of these amorphous materials in detail and figure out, you know, is it amorphous silica? Is it amorphous sulfate? But you're right, it is really interesting that there's so much amorphous material in here and that it is preserved over these timescales. I mean, granted, New Mexico is pretty arid, but also these you know things have been sitting there for quite a long time. So that's another aspect where we think this is a really exciting site, is that there is so much amorphous material that may be quite Mars relevant if we can pin down what it is. So yeah, we don't know yet, but we are hope to find out.
If there's time for a little bit of a follow-up question, you mentioned this being New Mexico and being arid, and I'm wondering how much you think modern groundwater interaction, that sort of thing, has changed these deposits since being at depth.
Good question. So a lot of this stuff was uplifted during the laramide orogeny. So that gives you an idea of how long it's been uplifted and how long it's been eroding. I don't have a good idea of what groundwater interaction is doing. I suspect it's mostly going to be meteoric water that is percolating down, partially because of, you know, we saw some recrystallization in these little fractures inside the dolomitic materials and the carbonate materials. But that's definitely a good thing to continue to look into as we continue looking at the site. Is, you know, there is still water in New Mexico, unlike on Mars, so we definitely need to take that into account going forward. So thank you for that.
Thank you, and thanks for your statements about trans people. It is great to hear. Thank you.
Got to stick together.
So I'll ask a question over here about beta carotene for our first speaker. I'm curious what your thoughts are about the potential preservation of beta carotene into the rock record. You're obviously looking at fresh material, right? So is that going to be an organic phase that might be expected into the rock record?
Well, actually, we know that's the hydromagnesite in the case. They are very much like capable to preserve the organics and any other organic matters. And I know that's the calcium carbonate phases as well. And also magnesium carbonates. There were some fossil records in some kind of the 2 gigabillion years ago. That's the carbonate deposits on Sweden that they have also actually consist some type of, the fossils the preserved in those type of the samples. And then of course, fossils are much more like the complex samples, but in the experimental wise and molecular scale, what I can say. I think the clay minerals, they are the best. Montmorillonite and nontronite, they are very best to preserve the carotenoids. And also I can say that was mainly with the temperature issue here with the hydromagnesite in my experiment. Hydromagnesite is also with the help of the ice can lock to beta carotene at -40, but -10 degree, that might be definitely related to type of the beta carotene. I have also made this analysis with the -10 degree data. And when I make the mapping, it was very complex. It was because of the beta carotene was like freely distributed at this temperature. So that's the issue is the magic here. The Avenger part is the ice. That's when it's formed at -40 degree. So in these temperatures, -40 and below, I believe, we can easily find any type of the beta carotene signatures in the magnesium, iron, smectite-rich rocks, and also in the carbonate deposits, hopefully.
Okay, thank you. So Any questions online? Okay. Well, I think we're done. I appreciate everyone sticking around. I appreciate our speakers and our audio video folks. And so thanks for staying and have a good evening. See you at posters.